Before we go anywhere tonight, you can let the day become smaller. There is nothing you need to solve, nothing you need to remember, nothing waiting inside these next few hours that requires you to stay awake. You can listen for as long as you like, and when the words begin to blur at their edges, you can let them. You do not have to follow every sentence. You do not have to hold every fact. You do not have to reach the end. Tonight is not a test. It is simply a journey, a very slow one. So let your breathing find whatever rhythm feels natural. There is no correct way to breathe, no special count, no technique to perform, just the quiet exchange that has been happening since before you knew how to name it. Air enters, air leaves, again and again. Perhaps you are lying in darkness. Perhaps there is a little light somewhere in the room, a doorway, a screen, a window. Perhaps the world outside is still moving, cars passing, buildings humming, water moving through pipes, electricity traveling silently through walls. Somewhere a refrigerator switches itself on, somewhere an elevator moves between floors, somewhere a pump begins turning because a sensor noticed that something had changed. You do not need to notice any of it. That is one of the quiet luxuries of being here. Most of the systems keeping you comfortable do not require your attention. Gravity holds you against the bed. The atmosphere remains around you. Warm air rises. Cool air falls. The room exchanges heat with the walls. Your breath leaves your face and mixes with the air around you. Water stays in a glass. Dust settles. A dropped object falls. The floor remains where you expect the floor to be. You can close your eyes. And for a while, the world continues without instruction. That is worth remembering, because tonight, very slowly, we are going somewhere where almost none of those assumptions can be trusted. But not yet. For now, stay here. Let your shoulders become heavy. Let your hands rest wherever they have chosen to rest. Let the muscles around your eyes stop trying to see through the darkness. There is nowhere else you need to be. The next thought can come, and it can go. The one after that can do the same. You are allowed to lose the thread. You are allowed to wake later and have no idea what part you missed. In fact, that would be perfectly appropriate, because the place we are eventually going to visit never truly sleeps. Machines remain awake there, fans turn, pumps circulate fluids, computers compare measurements, valves open and close, electric currents move through cables, water passes through filters, heat travels through metal, antennas listen, gyroscopes turn, and somewhere inside all of that machinery, a human being closes their eyes. For now, you can do the same. There is no urgency here, only distance, only darkness, only the slow preparation for a journey that begins a few 100 kilometers above the ground, where the word up has become strangely unreliable, where falling can continue for years, and where something as ordinary as breathing becomes an engineering problem. Imagine a person asleep, nothing unusual about that. Their eyes are closed, their body is tucked into a sleeping bag. There is no bed beneath them. There does not need to be. The sleeping bag is attached to a wall, although wall is already becoming a questionable word. Nearby, cables run through panels, small lights glow. A laptop screen has gone dark. Beyond several layers of metal, insulation and shielding, there is vacuum, no breathable atmosphere, no weather, no pressure that a human body can comfortably inhabit. Yet inside, the sleeper breathes, in and out, in and out. Each breath releases carbon dioxide. On Earth, the warm air around a sleeping person tends to move. Buoyancy helps create convection. Air circulates naturally as differences in temperature and density pull gases through the room. But here, the familiar arrangement is gone. There is no meaningful floor beneath the sleeper, no ceiling waiting above. Warm air does not simply rise in the ordinary terrestrial way. The carbon dioxide leaving the sleeper's mouth can linger nearby. Breath after breath, a small local cloud can begin to form. Not a cloud you could see, not a dramatic fog, just a region of air with more carbon dioxide than the astronaut would want to keep breathing. And so, somewhere nearby, a fan turns. That fan may sound like one of the least impressive machines ever sent into space. It does not have the spectacle of a rocket engine. It does not unfold into a golden telescope. It does not photograph another world. It simply moves air. Yet while the astronaut sleeps, that movement matters. And this gives us our question. Why does a space station need fans to keep a sleeping astronaut alive? It sounds almost absurd. A machine large enough to circle Earth, a laboratory assembled across decades, a structure supported by enormous solar arrays, a home that has hosted people continuously for years. And one of its most basic survival problems can begin with air that refuses to move away from a sleeping face. But that is the doorway, because once you ask why the fan matters, you have to ask where the carbon dioxide goes. And if carbon dioxide must be removed, you have to ask where fresh oxygen comes from. And if oxygen can be made from water, you have to ask where the water comes from. And if water is recycled, you eventually arrive at sweat, humidity, condensation, wastewater, and urine. Spaceflight has a remarkable ability to begin with stars and end with plumbing. Calm down, relax, settle in, subscribe. We're following this all the way to the edge. Then the questions continue. The machines cleaning the air require electricity. The electricity creates heat. The heat cannot simply be carried away by outdoor air because there is no outdoor air, so the station needs cooling loops. Those loops move heat toward radiators. The radiators must face space. The station must control its orientation. Controlling orientation requires another set of machines. Those machines interact with the station's orbit. The orbit slowly changes. The atmosphere, thin though it is at that altitude, creates drag. The station sometimes needs to be raised. Vehicles must arrive. Cargo must be transferred. Waste must leave. Parts fail. Filters clog. Experiments need power. People need food. Bones need loading. Muscles need resistance. Computers need cooling. Windows need protection. And every one of those systems must coexist inside a structure that is falling around Earth at extraordinary speed. So tonight, we are not going to treat a space station as a room floating in space. That description is too simple. A space station is closer to a carefully managed argument with the environment. The vacuum makes one demand, the human body makes another. Orbital mechanics adds its own rules. Heat behaves differently. Fluids behave differently. Fire behaves differently. Dust behaves differently. Even sleep becomes a systems problem. And through all of it, one quiet principle keeps returning. Nothing up here happens by itself. A breathable atmosphere does not remain breathable by itself. Water does not arrive by itself. Heat does not leave by itself. The station does not stay pointed in the correct direction by itself. Its orbit does not remain unchanged by itself. A visiting spacecraft does not simply pull into a parking space. And a sleeping astronaut's breath does not necessarily move politely away. Nothing up here happens by itself. So we will begin with the familiar shape, the bright panels, the long truss, the connected modules, the object many people have seen crossing the night sky as a moving point of light. And then, very slowly, we will go inside. We will follow the air. We will follow the water. We will follow the electricity. We will follow the heat. We will follow the forces that keep the entire structure falling without reaching the ground. And eventually, after travelling through pumps and pipes and gyroscopes and docking ports and radiators and recycling systems, we will return to one sleeping person and one turning fan. Let's begin. Familiar observation. From the ground, a space station can look almost disappointingly simple. A point of light, no visible laboratories, no solar arrays, no windows, no crew, just a bright object moving steadily against the stars. If you watch the International Space Station pass overhead, what you are really seeing is sunlight reflected from a sprawling orbital structure. It appears to cross the sky because it is moving rapidly around Earth. The station is not hovering. It is not balancing on some invisible shelf. It is falling, constantly. This is the first idea that must become comfortable. Orbit is a kind of continuous falling in which the ground curves away beneath the falling object. The station moves sideways so quickly that as gravity pulls it downward, the curved surface of Earth keeps dropping away. The result is not freedom from gravity. Gravity is still very much present. The station and everything inside it are falling together. This shared fall creates the condition commonly called microgravity. An astronaut floats because the astronaut is falling. The station floats because the station is falling. A loose pencil floats because the pencil is falling too. Everything is travelling together. This is why the first popular image of a space station can be misleading. We imagine a building placed in space, but a building on Earth is designed around stillness. Its foundation pushes against the ground. Its floors resist gravity. Its walls carry loads downward. Its plumbing depends heavily on the direction things fall. Its ventilation benefits from convection. Its toilets expect gravity to participate. Its sinks expect water to move toward drains. Its chairs expect bodies to remain on seats. Its shelves expect objects to remain on shelves. A space station inherits almost none of this convenience. It is a building whose architecture must function while the entire building falls, and that changes almost everything. The International Space Station was assembled from many major elements launched separately and connected in orbit. The first element, Zarya, launched in November of 1998. Soon afterward, the Unity connecting module was joined to it during a space shuttle mission. Over the following years, laboratories, nodes, airlocks, truss segments, solar arrays, radiators, robotic equipment, docking systems, and other components expanded the structure. This was not construction in the terrestrial sense. There was no crane standing on the ground beside the worksite. The worksite itself was circling Earth. Every new piece had to be launched. Every kilogram had to survive ascent. Every connection had to work in an environment where dropping a tool did not necessarily mean watching it land near your boot. The finished station became less like a single spacecraft built in one factory and more like an orbital neighborhood whose buildings arrived at different times. Its long central truss supports major external systems. Solar arrays collect sunlight, radiators reject unwanted heat. Pressurized modules provide places where people can live and work without spacesuits. Docking ports allow visiting spacecraft to arrive. Robotic systems help move equipment. External experiments are exposed directly to the space environment. Inside, the appearance changes. The heroic silhouette disappears. You find cables, storage bags, labels, laptops, handrails, ventilation grills, equipment racks, food packages, exercise machines, cameras, tools, and a surprising amount of stuff attached to surfaces. This is not untidiness in the ordinary sense. In microgravity, a table is not automatically more useful than a wall. A ceiling can become storage. A wall can become a workstation. A person can rotate and decide that another surface now feels like the floor. The architecture is three-dimensional in a way most rooms on Earth are not. Yet the human brain still enjoys orientation. Crews often maintain visual conventions. Equipment is arranged in ways that help people understand where they are. Labels matter, lighting matters, color matters. A station can be physically navigable in every direction while still being psychologically easier to use when there is some shared idea of up and down. And inside this strange building, the air is moving. It has to. This brings us back to our sleeping astronaut. Why does a space station need fans to keep a sleeping astronaut alive? Because the absence of ordinary buoyancy-driven convection changes the behavior of gases around the body. On Earth, exhaled breath mixes with room air through a combination of motion, diffusion, and convection. In microgravity, forced ventilation becomes essential. Fans circulate cabin air. Ventilation carries carbon dioxide away from local regions. The air is then processed by life support equipment. This is one of the first great reversals of living in orbit. On Earth, we usually think of a fan as comfort, a breeze, a way to feel cooler. In a space station, airflow is part of survival infrastructure. It helps prevent stagnant pockets. It carries heat. It moves contaminants towards systems designed to remove them. It makes the atmosphere inside the station behave more like an atmosphere and less like a collection of invisible local neighborhoods. Nothing up here happens by itself. Even the air must be persuaded to travel. The station's atmosphere is not simply loaded before launch and left alone. Humans continuously change it. Every breath consumes oxygen and produces carbon dioxide. Every person releases water vapor. Equipment releases heat. Materials can release trace chemicals. Experiments may introduce their own contaminants. Particles float rather than settling neatly onto a floor. The atmosphere, therefore, has to be watched, moved, filtered, cleaned, rebalanced. The station is not merely containing air, it is managing air. And this distinction is the beginning of understanding how almost every space station works. A pressure vessel gives you a boundary. Life support gives you a habitat. Those are not the same thing. A sealed metal cylinder filled with air may remain habitable for a while, but people are chemical engines. They breathe, drink, eat, sweat, shed skin, produce waste, generate heat, release moisture, and expect to do all of this continuously. A long-duration station must therefore become partly regenerative. It must recover useful resources where possible. It must remove harmful byproducts. It must replace what cannot be recovered. It must detect failures before those failures become larger problems. And it must do this while remaining repairable by the people living inside it. That final point matters. A space station is not a sealed appliance. It is a machine inhabited by its own maintenance crew. Astronauts replace filters, repair equipment, install upgrades, move cargo, inspect systems, respond to alarms, perform experiments, exercise, prepare food, sleep, and occasionally spend hours searching for an object that has floated into a place no sensible terrestrial object would ever choose to visit. The familiar observation, then, is that a space station is a home and laboratory in orbit, but that is only the outer shell of the answer. The more useful observation is quieter. A space station is a place where ordinary background processes have been turned into machinery. On Earth, gravity moves water downhill. In orbit, pumps must often decide where water goes. On Earth, warm air rises. In orbit, fans move the atmosphere. On Earth, the planet's vast atmosphere dilutes the carbon dioxide from one sleeping person. In orbit, the cabin is finite. On Earth, heat can pass into surrounding air. In orbit, excess heat must eventually be radiated away. On Earth, a building can remain where it was constructed. In low Earth orbit, a station encounters a trace of atmosphere and gradually loses altitude unless its orbit is periodically adjusted. The station works because engineers identified processes that Earth normally provides for free and replaced them with systems. This is the hidden architecture, not the modules, not the solar arrays, not the truss. The hidden architecture is the chain of dependencies. Air depends on circulation. Circulation depends on electricity. Electricity produces heat. Heat depends on cooling. Cooling depends on pumps. Pumps depend on power. Power depends on sunlight and energy storage. The orientation of the solar arrays matters. The orientation of the station matters. The orbit matters. Visiting vehicles matter. Ground control matters. Maintenance matters. Everything touches something else. And somewhere inside that web, a person is asleep, breathing in, breathing out, trusting a fan they may barely notice. So the familiar question is not really how people live in space. That question is too broad. The more interesting question is how a machine can continuously recreate enough of Earth's invisible services to let a human body forget, for a few hours at a time, that it is living inside a spacecraft. And beneath that question waits our smaller one. Why does a space station need fans to keep a sleeping astronaut alive? We have found the first part of the answer. Because in orbit, air does not behave quite the way a bedroom has taught us to expect, but moving the carbon dioxide away from a face only moves the problem. The gas still exists. It is now somewhere else inside the station. So where does it go? Let's go find it. The carbon dioxide has moved away from the sleeping astronaut. That sounds like progress, and it is, but only in the smallest sense. The fan has solved a local problem by creating a larger one. The gas is no longer gathering near one person's face. Now it is mixed into the shared atmosphere of the station. It has joined the air moving through passageways, laboratories, sleeping quarters, equipment bays, and ventilation ducts. The astronaut continues breathing. So does everyone else. Carbon dioxide continues entering the cabin, breath by breath, minute by minute, hour by hour, and because the station is a sealed environment, there is no open window, no breeze from outside, no forest nearby, no enormous planetary atmosphere waiting to dilute the waste gas until it becomes someone else's problem. The carbon dioxide must be dealt with. This is where our original question changes. Why does a space station need fans to keep a sleeping astronaut alive? At first, the answer seemed to be airflow. The fan prevents exhaled carbon dioxide from lingering around the face, but airflow does not destroy carbon dioxide. It only transports it. The real question is therefore not how to move bad air away from a person. The real question is what to do with the bad air after it has been moved. That distinction matters. Imagine sweeping dust from the center of a room into a corner. The room may look cleaner from where you are standing, but the dust has not disappeared. You have changed its location. A space station cannot survive for long by endlessly rearranging its waste. Eventually, something must be removed, recovered, stored, transformed, or sent away, and carbon dioxide is only the beginning. The station must also deal with humidity, trace gases, odors, particles, heat, microorganisms, and the ordinary chemical consequences of having several human bodies living inside a relatively small enclosed environment. The atmosphere is shared. That makes every breath part of a common system. On Earth, you rarely think about where the carbon dioxide from your last breath will go. The answer is wonderfully complicated. It mixes into the atmosphere. It may eventually be absorbed by an ocean. It may enter a plant. It may remain in the atmosphere for a very long time. The planet gives your breath room to become anonymous. A space station does not. Inside a spacecraft, your breath remains part of the engineering problem. The air leaving your lungs contains more carbon dioxide than the air entering them. It also contains water vapor. It is warm. It changes the atmosphere around you. Multiply that by a crew, then continue all day, then continue all night, then continue for weeks, months, years. The cabin atmosphere must be managed continuously. Nothing up here happens by itself. The air is therefore pulled through machinery designed to separate unwanted carbon dioxide from the gases the crew still needs. On the International Space Station, carbon dioxide removal has relied on systems using materials that can selectively capture gas molecules. One important system is the carbon dioxide removal assembly. Its name is wonderfully direct. There is little poetry in life support engineering. That may be because the poetry is already hiding inside the plumbing. The carbon dioxide removal assembly uses molecular sieve materials. These materials can separate and capture gases according to their physical properties. Cabin air passes through the system. Carbon dioxide is removed. The cleaned air can return to the cabin. The captured carbon dioxide must then be released from the material so that the material can be used again. This is an important difference between a disposable filter and a regenerative system. A disposable filter eventually fills. Then someone must replace it. That may be acceptable in a house. It becomes less attractive when every replacement has to arrive on a rocket. So engineers prefer systems that can repeatedly capture and release what they are removing. The machinery cycles. One part may be collecting carbon dioxide while another is being regenerated. Heat and pressure changes help free the captured gas. The system repeats the process again and again. The atmosphere circulates, carbon dioxide enters the machinery, cleaner air returns, and the sleeping astronaut continues breathing. But now the question becomes stranger, because carbon dioxide is not merely waste, it contains oxygen, the crew needs oxygen, so a station that throws away all of its carbon dioxide is also throwing away atoms that might be useful. This is the deeper hidden question. How much of a human being's waste can a spacecraft turn back into supplies? That is the question beneath almost every long-duration space station. It is also the question that separates a temporary capsule from something closer to a habitat. A short mission can carry what it needs. A longer mission begins to encounter the tyranny of replacement. Every litre of water used must come from somewhere. Every kilogram of oxygen consumed must come from somewhere. Every filter eventually needs attention. Every spare part occupies mass and volume. Every resupply flight has limits. The farther humans travel from Earth, the more severe this becomes. A station in low Earth orbit can be supplied from the ground. A future habitat around the Moon is farther away. A spacecraft travelling toward Mars cannot expect a delivery vehicle to arrive next week. With a replacement pump and several containers of drinking water, distance turns recycling from an efficiency into a survival strategy. And so the hidden question inside a space station is not simply how to keep people alive, it is how to make yesterday's waste participate in tomorrow's survival. Consider the path of oxygen. An astronaut breathes oxygen, the body uses it. Carbon dioxide is produced. The astronaut exhales, a fan moves the exhaled gas away. The station's ventilation system carries it through the cabin. Carbon dioxide removal equipment separates it from the atmosphere. At this point, the carbon dioxide can be treated as waste, or some of its ingredients can be recovered. This is where the machinery begins to resemble a small artificial ecosystem. Not a complete ecosystem, not a forest in a metal tube, but a collection of engineered loops. One loop touches another. Water becomes oxygen. Oxygen enters a person. A person produces carbon dioxide. Carbon dioxide can help produce water. That water can return to the system. The circle is imperfect, but every time the circle closes a little more, less material has to arrive from Earth. The International Space Station has used oxygen generation equipment that splits water into oxygen and hydrogen. The oxygen enters the cabin atmosphere. The crew breathes it. The hydrogen becomes useful elsewhere in the system. Meanwhile, carbon dioxide removed from the cabin can be combined with hydrogen in a process based on a reaction known as the Sabatier reaction. The products include water and methane. The water can be recovered. The methane has traditionally represented a loss from the loop and can be discarded, so the system is not perfectly closed. Some useful material still escapes. Some supplies still have to be replaced. But something remarkable has happened. The crew breathes oxygen. Their bodies help convert that oxygen into carbon dioxide. The station captures the carbon dioxide. Other machinery helps recover part of what would otherwise have been lost. Water reappears, and water can once again become a source of oxygen. A breath has entered a machine, and part of that breath has begun travelling back toward another breath. Nothing up here happens by itself. This is not recycling in the casual sense of placing a bottle in a different bin. It is molecular bookkeeping. Every useful atom matters. The station cannot create matter from nothing. It can only move matter through different forms: water, oxygen, hydrogen, carbon dioxide, methane, waste, recovered resource. The labels change, the atoms remain. This is why a long-duration spacecraft is fundamentally different from a sealed room. A sealed room has supplies. A spacecraft needs cycles. The better the cycles become, the less dependent the crew becomes on constant replacement. But perfect recycling is extraordinarily difficult. Every loop leaks somewhere, not necessarily through a literal hole. A system can lose useful material because a chemical process produces a waste product that cannot yet be efficiently recycled. Water can remain trapped in waste. Gases can be vented. Filters and equipment need maintenance. Humans consume food that must still come from somewhere. The station is therefore not a completely closed world. It is a partially closed one, a world with deliveries. And that distinction becomes clearer when we follow another substance: water. Water is heavy, not emotionally. Although after carrying enough of it, perhaps emotionally too. Water has mass. Launching mass into orbit requires energy, hardware, fuel, and money. If a crew uses water once and discards it, replacement water must eventually be launched. For a short mission, this may be manageable. For continuous habitation, it becomes wasteful. So a space station tries to recover water from places that a person on Earth might prefer not to think about while drinking breakfast coffee: humidity, sweat, breath, wastewater, and urine. The human body releases water continuously. Every exhalation contains moisture. Every exercise session adds humidity to the cabin. Water vapor enters the air. In a terrestrial room, some of it may leave through ventilation. Some may condense. Some may simply become part of the enormous atmospheric system around the building. In a space station, moisture is a resource. Cabin air passes through equipment that can remove humidity. Water vapor condenses. The The collected water enters processing systems. Wastewater from other sources joins the recovery chain. Urine can also be processed to recover water. This is one of the facts about spaceflight that tends to produce a predictable reaction. People hear that astronauts drink recycled urine. Then the entire life support system is reduced to one slightly alarming sentence. But that sentence misses the interesting part. The astronaut is not drinking urine, the astronaut is drinking water. The system's job is to separate the water from everything that made the original liquid unsuitable to drink. On Earth, this happens too. Water has been inside organisms before. It has moved through soil, rivers, clouds, animals, plants, sewage systems, treatment plants, oceans. The water cycle has never been particularly sentimental about previous ownership. A space station simply makes the cycle smaller, faster, and much more visible. The water recovery system aboard the International Space Station processes wastewater and recovered moisture so that water can be reused. The result supports drinking and other needs. The goal is not to preserve the identity of the original liquid. The goal is to recover water molecules. This distinction is comforting. Or at least, it becomes comforting after a while. The station is full of these transformations. Something unpleasant becomes useful. Something invisible becomes measurable. Something that would normally be discarded becomes valuable because Earth is hundreds of kilometers below. This changes the meaning of waste. On Earth, waste often means something that leaves your immediate environment. A rubbish truck arrives. A drain carries water away. An exhaust pipe releases gas. The object disappears from your personal world. But disappearance is usually geography. The waste went somewhere. A spacecraft removes the geographical illusion. There is no somewhere else inside a sealed habitat. Every output has to be considered. Every gas, every liquid, every solid, every bit of heat, every floating particle. The station is a lesson in consequences, a quiet one, a mechanical one, a lesson told by filters and pumps. This brings us back to the sleeping astronaut. Why does a space station need fans to keep a sleeping astronaut alive? Because the first step in controlling a closed atmosphere is moving that atmosphere. A carbon dioxide removal system cannot clean gas that never reaches it. A sensor cannot accurately describe a cabin if the cabin contains stagnant pockets that differ from one another. Heat cannot be distributed properly if air remains still. Humidity must reach equipment that can remove it. Trace contaminants must travel toward filters. The fan is not merely blowing air. It is connecting the astronaut to the life support system. That is the hidden function. The ventilation network turns many local atmospheres into one manageable atmosphere. Without circulation, the station would not have one cabin environment. It would have countless small environments. A warm pocket near electronics. A humid pocket near exercise equipment. A carbon dioxide rich pocket near a sleeping face. A stagnant region behind equipment. A moving region near a vent. The fan stitches these regions together. It makes the atmosphere available to the machines responsible for maintaining it, and the machines in turn depend on other machines. The carbon dioxide removal equipment needs power. The oxygen generation equipment needs water and power. The water recovery equipment needs power. Pumps need power. Sensors need power. Computers need power. Fans need power. The hidden question has therefore moved again. We began with air. Now we have arrived at electricity. This happens constantly when trying to understand a space station. You follow one system and discover that it is standing on another. Then you follow that system and find another beneath it. There is no single machine called life support. There is a network. A fan can protect a sleeping astronaut only if electricity reaches the fan. Electricity can reach the fan only if the station generates and distributes power. Power generation creates heat. Heat must be moved. The station's orientation affects how sunlight reaches its solar arrays. Its orientation must be controlled. Its orbit must be maintained. The chain continues. Everything touches something else. And yet, before we follow the electricity, we need to remain with the atmosphere a little longer. Because cleaning air is not the same as making air safe. A station must also maintain pressure. It must maintain enough oxygen. It must monitor carbon dioxide. It must remove trace contaminants. It must manage humidity. It must detect smoke. And it must do all of this inside a structure surrounded by vacuum. The pressure difference between the cabin and space is always present. The atmosphere wants to escape. The station's walls prevent it. Every hatch, every seal, every window, every connection between modules, every docking interface, every penetration through the pressure shell, all of them participate in the same task: keep the atmosphere inside. This is easy to say. It is harder to appreciate. On Earth, the air inside a building and the air outside it are at broadly similar pressures. A wall may keep out rain, wind, heat, cold, noise, but it does not usually have to prevent the entire atmosphere of the room from escaping into a vacuum. A space station's pressure shell does. The cabin air pushes outward, the structure holds inward, continuously. There is no pause, no nighttime setting, no moment when the pressure difference becomes bored and leaves. The station must remain sealed while people live inside it, and yet it cannot simply be a perfect, unopened container. People need to arrive, people need to leave. Cargo must enter, experiments must move, spacewalks must happen, vehicles must dock, modules must connect. So the station must do something wonderfully difficult. It must be sealed and accessible, strong and repairable, closed and full of doors. Every hatch is therefore part of a pressure boundary. When a spacecraft docks, the connection must become airtight before hatches open. When astronauts prepare for a spacewalk, an airlock allows them to move between the pressurized station and vacuum without emptying the entire station's atmosphere into space. The airlock is a controlled transition between worlds. Inside one side, shirts, socks, laptops, food, breathable air. On the other, a spacesuit, vacuum, extreme thermal conditions, and orbital daylight bright enough to carve hard shadows across metal. The hatch between them is not merely a door, it is a boundary between two environments that cannot be allowed to mix freely. The same principle applies throughout the station. Boundaries matter, flow matters, pressure matters, and the atmosphere must remain within limits narrow enough for human bodies and equipment to function. This introduces another hidden difficulty. The station is not static. People move. Hatches open between modules. Vehicles arrive. Vehicles depart. Experiments operate. Crew size changes. Equipment releases gases. Leaks, even very small ones, must be monitored. The atmosphere is a living engineering problem. Not living in the biological sense, but changing, always changing. Sensors watch, computers record. Crew members inspect. Ground teams analyze. The station continuously asks a quiet series of questions. How much oxygen is present? How much carbon dioxide? How much pressure? How much humidity? What contaminants are appearing? Is the air moving where it should? Is a filter becoming loaded? Is a fan performing normally? Is a reading unusual because the environment changed, or because the sensor did? This is the part of spaceflight that rarely appears in dramatic paintings. A spacecraft survives through measurement. A station cannot rely on intuition. You cannot smell every dangerous gas. You cannot feel a slow pressure loss immediately. You cannot look at a wall and know the exact composition of the atmosphere. So the station turns invisible conditions into numbers. Sensors become artificial senses. They extend the crew's awareness into places human perception cannot reliably reach. And then, the crew must trust them. This is another kind of loop. A machine measures the environment. A person or computer interprets the measurement. A system responds. The environment changes. The machine measures again. The station is always listening to itself. Fans create airflow. Sensors watch the atmosphere. Carbon dioxide removal equipment cleans it. Oxygen generation equipment replenishes what the crew consumes. Water recovery equipment retrieves moisture that would otherwise be lost. Chemical processing can recover additional resources. And all of this exists because the station has no river, no weather, no soil, no open atmosphere, no natural water cycle large enough to forgive inefficiency. So engineers built small artificial cycles instead. The cycles are not perfect, but perfection is not required. Reliability is, repairability is, redundancy is, the ability to continue after something fails is, because eventually something will. A valve may stick, a filter may clog, a pump may stop, a sensor may drift, a seal may degrade, a component may reach the end of its designed life. A space station is not a machine that never breaks. It is a machine designed around the knowledge that machines break. That is a much more interesting achievement, and it leads us toward the next part of the story, the real constraint, the rule that shapes every system we have encountered. The reason a station cannot simply carry endless tanks of oxygen, endless containers of water, endless replacement filters, endless spare machines. The reason recycling matters, the reason efficiency matters, the reason 1 kilogram can become the subject of years of engineering. The station may appear to float effortlessly above Earth, but nothing about getting material there is effortless. Everything inside the station had to come from somewhere: the fan, the filter, the water processor, the food package, the laptop, the sleeping bag, the bolt, the spare valve, the oxygen, the first modules themselves. Before any of them could become part of life in orbit, they had to climb. And climbing away from Earth is expensive in the most fundamental currency of spaceflight: mass. The atmosphere has shown us the hidden question. Now the launch vehicle will show us the constraint. Let's go find it. There is a peculiar habit in space engineering. People weigh things, then they weigh them again. A component becomes lighter. Someone celebrates. A bracket loses a little mass. Someone notices. A cable route changes. A tank becomes smaller. A structure becomes thinner where it can safely become thinner. A machine that would seem compact on Earth may still be considered too heavy for flight. This obsession can appear excessive until you remember one simple fact. Nothing begins in orbit. At least, not yet. Every station module, every solar array, every computer, every bag of food, every litre of replacement water, every experiment, every spare part, every human being, all of it begins deeper inside Earth's gravitational field. To reach orbit, it must be accelerated to extraordinary speed. A launch vehicle does not merely lift a spacecraft upward, it must give that spacecraft enough horizontal velocity to keep falling around Earth. This is the constraint beneath the station. Mass must be launched, and launching mass requires more than adding a slightly larger engine. A rocket must carry propellant, but carrying more propellant adds mass. That additional mass may require still more propellant. The vehicle must lift its payload, its structure, its engines, and for much of the journey, the propellant it has not yet burned. This is why rockets use stages. A stage that has completed its work can be discarded. The remaining vehicle no longer has to accelerate empty tanks and engines that are no longer useful. The rocket becomes lighter as it climbs. The station, by contrast, must remain. Once a piece reaches orbit and becomes part of the habitat, its mass is now part of everything that follows. It affects how the station responds to forces, how it is controlled, how its orbit is adjusted, how new modules can be attached, how visiting vehicles interact with it. Mass is not simply a launch problem, it remains part of the station's physical identity. This is why our hidden question about recycling becomes unavoidable. Suppose a station did not recover water. Every drink would require replacement water from Earth. Every use would reduce the stored supply. The longer the mission, the more water would have to be launched. Suppose the station did not generate oxygen. Breathing would slowly empty stored oxygen supplies. More oxygen would have to arrive. Suppose every carbon dioxide filter worked only once. Used filters would accumulate. New filters would have to be launched. Suppose every broken component required immediate replacement from the ground. The station would become dependent on a constant chain of deliveries. For a station close to Earth, some resupply is possible. For a station farther away, dependence becomes more dangerous and more expensive. So the constraint is not merely mass, it is dependence. Every resource that cannot be recovered becomes something that must be replaced. Every system that cannot be repaired becomes something that must be duplicated or resupplied. Every kilogram launched carries a history of fuel, structure, planning, testing, and risk. Nothing up here happens by itself. The station therefore lives between two competing desires. Bring everything you might need, and bring as little as possible. Those desires do not get along. A crew wants spare parts, engineers want redundancy, scientists want experiments, astronauts need food, life support systems need equipment, maintenance requires tools, medical supplies occupy space, computers need replacements, clothing has mass, packaging has mass, even rubbish has to go somewhere after the useful contents are gone. A station cannot be infinitely large, a launch vehicle cannot carry infinite mass, so every mission becomes an exercise in selection. What must be launched? What can be reused? What can be repaired? What can be shared? What can be made smaller? What can be made lighter? What can be produced in orbit? What can be recovered from waste? This constraint reaches into the design of almost everything. Consider water again. Water is useful in so many ways that carrying it may seem unavoidable. The crew drinks it. Food preparation may require it. Hygiene requires it. Oxygen generation can use it. Scientific experiments may need it. But water is heavy, so recovery becomes valuable. The more water the station can reclaim from humidity and wastewater, the less replacement water must be launched. The same logic applies to oxygen. If water can be split to provide oxygen, stored oxygen is not the only option. If some oxygen can be recovered indirectly from carbon dioxide, the loop becomes tighter still. The system begins to squeeze more usefulness from the same atoms. This is not because engineers have developed a philosophical objection to waste, it is because rockets make waste expensive. The constraint also shapes the station's physical structure. A pressure vessel must be strong enough to contain the atmosphere, but stronger structures often require more material. More material means more mass. More mass means more launch burden. So the structure must be strong, but not unnecessarily heavy. Protective shielding must reduce risk from small orbital debris and natural micrometeoroids, but shielding adds mass. Radiation protection is valuable, but shielding adds mass. Redundant systems improve resilience, but duplicate hardware adds mass. Larger living volume improves comfort and can support more equipment, but larger modules require more structure, more atmosphere, more thermal control, more launch capacity. Every improvement has a shadow. This is one of the central truths of spacecraft design. There is rarely a perfect solution. There are trades. You gain something, you pay somewhere else. A thicker wall may improve protection but increase mass. A more powerful machine may perform better but require more electricity. More electricity may require larger power systems. Those systems may create more heat. More heat may require greater cooling capacity. Greater cooling capacity adds pumps, fluid, pipes, radiators, structure, and control systems. One decision spreads, everything touches something else. This is why the station cannot be understood as a collection of independent machines. It is a web of compromises. The fan beside the sleeping astronaut is connected, conceptually and physically, to the launch vehicle that once carried its parts from Earth. If the fan consumes electricity, the power system must provide it. If the fan releases heat, the thermal control system must eventually reject that heat. If the fan fails, another fan or replacement part may be needed. If the fan is too loud, the crew may sleep poorly. If it is too weak, airflow may become inadequate. If it is too heavy, launch mass increases. If it vibrates, that vibration may affect sensitive experiments. Even a fan has politics, quiet mechanical politics, a negotiation among airflow, noise, power, mass, reliability, maintenance, and human comfort. The same is true of almost every object aboard the station. A space station works because thousands of these negotiations were made before launch, and continue to be made during operation, but mass is only one part of the constraint. The station also has limited volume. Inside a pressurized module, space is valuable. Equipment racks occupy room. Storage occupies room. Crew movement requires clear paths. Ventilation requires open routes. Emergency access must remain possible. Experiments need workspace. Food needs storage. Waste needs temporary storage. spare parts need homes. And in microgravity, objects have a talent for becoming nomadic. A loose item can float, a bag can migrate, a tool can disappear behind equipment. So storage is not merely about having enough volume, it is about controlling objects in 3 dimensions. Everything must be attached, contained, velcroed, strapped, latched, bagged, or deliberately allowed to float for a reason. On Earth, gravity is a free storage assistant. Put a cup on a table, it remains there. Put a tool in a drawer, it rests at the bottom. Put food on a shelf, the shelf supports it. In orbit, the station must replace this simple certainty with attachment. The result is an interior that can appear densely packed. Surfaces become useful, walls hold bags, ceilings hold equipment, labels become essential. The idea of a floor becomes partly conventional, and yet the volume cannot simply expand without consequence. A larger pressurized volume requires a larger pressure vessel, more structure, more launch mass, more atmosphere, more surfaces, more ventilation, more monitoring, more maintenance. Again, everything touches something else. Time is another constraint. A crew member has only so many hours in a day. Astronaut time is a resource. Every repair consumes it. Every maintenance task consumes it. Every inventory search consumes it. Every filter replacement, every inspection, every experiment setup, every exercise session, every cargo transfer. A system that saves mass but requires constant human attention may not actually be the better system. A machine that is extremely efficient but difficult to repair may create another problem. A component hidden behind several equipment racks may take longer to reach. A maintenance procedure may require tools, replacement parts, coordination with ground teams, and careful shutdown of connected systems. So station engineering must consider not only whether a machine works, but whether people can live with the work of keeping it working. This is why reliability is not merely a number, it becomes part of daily life. A reliable machine gives time back to the crew. A troublesome machine becomes a resident. A demanding one. The station has another limited resource, power. Sunlight is abundant in orbit, but electricity is not automatically abundant. Solar arrays must convert sunlight into electrical power. The power must be conditioned, distributed, stored for periods when the station passes through Earth's shadow, managed among many users. Life support competes with experiments. Computers compete with heaters. Pumps compete with exercise equipment. Communication systems need power. Lights need power. Every electrical device eventually contributes heat, and heat becomes another constraint. This is where the logic of the station begins folding back on itself. A machine solves one problem and creates heat. A cooling system solves the heat problem and requires power. The power system solves the electricity problem and requires large external hardware. That hardware affects the station's structure and orientation. Orientation control requires its own systems. Those systems require power and maintenance. The station is a chain of solutions that produce new engineering questions. This is not failure. This is engineering. The absence of problems is not the goal. The goal is to create problems you know how to manage. A fan is easier to manage than a stagnant cloud of carbon dioxide. A carbon dioxide removal machine is easier to manage than an increasingly toxic atmosphere. A water recovery system is easier to manage than launching every drop of water forever. A cooling loop is easier to manage than allowing electronics and people to overheat. A solar array is easier to manage than carrying all the station's lifetime energy in batteries. Each solution introduces complexity, but it replaces a worse constraint. The art lies in choosing which complexity you are willing to live with, and no constraint is more absolute than the environment outside. Vacuum. The station cannot use outside air for cooling. It cannot open a vent and invite in a breeze. It cannot draw oxygen from the surroundings. It cannot dump wastewater into a municipal system. It cannot send a technician outside in ordinary clothes. The external environment provides sunlight, a view, a place to radiate heat, and very little forgiveness. So the station must carry its environment with it. This is perhaps the simplest definition of a crewed spacecraft, a machine that carries a small piece of habitability through a place that does not provide it. Air, pressure, temperature, water, power, protection. All enclosed within systems, light enough to launch and reliable enough to trust. The constraint is severe, but it produces elegance, because once mass, volume, power, time and resupply are limited, waste begins to look different. A drop of humidity is no longer merely dampness, it is recoverable water. Carbon dioxide is no longer only an unwanted gas, it contains atoms that may be useful. A visiting cargo vehicle is not merely transportation, it may become temporary storage. A departing vehicle may carry waste. A module is not merely a room. Its walls are structure, pressure boundary, attachment surface, cable route, thermal environment, and part of a larger vehicle. A sleeping compartment is not merely a bedroom, it is a place where ventilation must be carefully maintained. The constraint teaches the station to make one thing perform many jobs. And this brings us back again. Why does a space station need fans to keep a sleeping astronaut alive? Because the station cannot afford to solve breathing by simply carrying an endless supply of fresh air and discarding the old atmosphere. The air must be circulated, measured, cleaned, replenished, reused. The fan is one small part of a system built under the pressure of scarcity. The station cannot depend on infinity. Not infinite air, not infinite water, not infinite power, not infinite storage, not infinite replacement parts. It must live inside limits. And now, we can see what happens if those limits are ignored. A fan stops, airflow changes, a filter becomes less effective, carbon dioxide rises, a cooling loop loses performance, heat accumulates, a power channel fails, equipment must be shut down, a leak appears, pressure begins to fall, a visiting vehicle cannot dock, supplies are delayed, a toilet fails, a pump stops, a computer resets. None of these problems exists alone. The station is connected too deeply for that. The real danger is not always one dramatic failure. Sometimes it is a cascade. A small problem changes the conditions for another system. That system responds. Resources are redirected, crew time is consumed, redundancy is reduced. The station continues, but with fewer options. This is the problem in full, not merely keeping a machine running. Keeping a network of dependent machines functioning while people live inside the network, and while the entire network circles Earth. The constraint has given us the shape of the challenge. Now we need to see what breaks when the shape is disturbed. Let's wonder about it. A space station is easiest to understand when everything is working. The fans hum, the lights glow, water appears when needed, computers respond, the air feels ordinary, and that ordinariness is the achievement. A successful life support system is almost invisible. It creates normality inside an abnormal place. But to understand the station fully, we have to remove that normality one layer at a time, not dramatically, not all at once, just slowly. Imagine the airflow weakening. The first change may not look like anything. Air is invisible, carbon dioxide is invisible. The sleeping astronaut still appears to be sleeping, but the local environment around the face begins to change. Exhaled gas is not carried away as effectively. The astronaut may begin rebreathing more carbon dioxide. The body notices chemistry long before the eyes notice machinery. A headache may appear. Breathing may become uncomfortable. Sleep may be disturbed. The problem is not that the station suddenly has no oxygen anywhere. The problem is that the atmosphere is no longer being managed evenly where the person actually is. This is why local airflow matters. A station can have acceptable, average atmospheric conditions and still contain poorly ventilated regions. The body does not breathe an average. It breathes the air directly around the nose and mouth. This is our strange question in its sharpest form. Why does a space station need fans to keep a sleeping astronaut alive? Because survival happens locally. A sensor elsewhere in the module cannot breathe for you. A tank of oxygen somewhere in the station cannot help if breathable air is not reaching your face. A carbon dioxide removal machine cannot remove gas that ventilation never delivers to it. The atmosphere must be connected. The fans create that connection. Now imagine that airflow continues, but carbon dioxide removal weakens. The cabin atmosphere is still mixing. This time, that mixing spreads the problem evenly. Carbon dioxide produced by the crew accumulates faster than it is removed. The station's sensors begin to notice. The crew and ground teams can respond. Backup systems may be used. Operating conditions can be adjusted. Repairs can begin. But the important point is this: the station is not safe because nothing fails. It is safe because failures are detected, understood, and managed. Redundancy buys time, monitoring buys awareness, procedures buy order, spare parts buy options. Crew training turns those options into action. This is the deeper machinery of a space station, not metal, not electronics. Preparedness. Now imagine a different problem. The air is clean, but oxygen generation is unavailable. The crew does not immediately stop breathing. The station has reserves and other ways of managing atmospheric oxygen. A failure in one system does not necessarily become an immediate emergency. That is the purpose of layered capability. But the station has begun spending a limited resource: time. How long can the current configuration continue? What backup supplies are available? What repairs are possible? When is the next visiting vehicle? Can other systems compensate? A space station failure is often a question of clocks. Not one clock. Several. The oxygen clock, the water clock, the power clock, the thermal clock, the crew time clock, the spare parts clock, the orbital clock. Good operations are partly the art of making sure none of these clocks reaches zero. Now imagine the water recovery system losing capability. Again, the crew does not immediately become thirsty. Stored water exists, resupply may be available. Other operational choices can reduce consumption, but the station becomes more dependent on what it already has and what can arrive later. A closed loop has opened. Material begins flowing in only one direction, from stored supply, to use, to waste. The longer the loop remains open, the more replacement material is required. This is why regenerative systems matter. They slow the clocks. They turn a limited stock into a circulating resource. But regenerative systems create their own maintenance burden. Filters need attention, pumps wear, valves move, sensors age, chemical beds cycle, surfaces become contaminated. The station survives by constantly repairing the machines that make survival less dependent on resupply. There is a gentle absurdity in this. The more self-sufficient a spacecraft becomes, the more machinery it may need in order to become self-sufficient, and every new machine becomes something else that can fail. This is the central tension of long-duration spacecraft design. Complexity can create resilience. Complexity can also create failure points. The answer is not to eliminate complexity. The answer is to organize it. Separate functions where useful. Provide backups. Design for maintenance. Monitor performance. Train the crew. Keep spare parts. Learn from failures. Improve the next generation. The International Space Station is not simply a finished object. It has been a long-running experiment in how machines and people maintain one another. The crew maintains the station. The station maintains the environment that maintains the crew. A loop again. Always a loop. Nothing up here happens by itself. Now imagine the power system losing part of its capacity. This is where the web becomes visible. A reduction in available electrical power may require equipment to be turned off. But which equipment? Life support is essential. Communications matter. Thermal control matters. Computers matter. Experiments may be paused. Non-essential loads may be reduced. The station changes configuration. It becomes, temporarily, a different machine. This ability to reconfigure is part of resilience. A rigid system has one way to work. A resilient system has several acceptable ways to continue. The same principle appears in the station's thermal systems. Every person produces heat. Every computer produces heat. Every motor, every light, every electrical conversion. Heat accumulates inside the pressurized modules. On Earth, a building can transfer heat to surrounding air. A fan can move indoor air across a surface, and eventually the environment outside the building can absorb the energy. A space station cannot rely on surrounding air. There is essentially none. Vacuum is not a cold wind. It does not blow across the station and carry heat away. This is one of the most persistent misunderstandings about space. Space may be described as cold, but cooling something in vacuum can be difficult. Without air, convection to the surroundings disappears. Heat must move through the station by conduction within materials, by circulating fluids, and ultimately by thermal radiation. So the station needs another chain. Heat must be collected, transported, moved toward external radiators, and radiated away into space. If that chain fails, heat remains. The problem in full is therefore not merely generating enough power, it is surviving the consequences of using power. Every useful electrical device eventually becomes part of the thermal problem. A laptop performing an experiment becomes heat. A pump moving water becomes heat. A fan keeping an astronaut safe becomes heat. The station must dispose of the energy it has already used. This is a beautiful reversal. On Earth, we often struggle to keep heat. In orbit, the station must carefully throw it away. And throwing away heat requires large external surfaces, radiators. These surfaces are designed to emit thermal energy into space, but they must operate while the station moves through sunlight and shadow. They must coexist with solar arrays. They must avoid configurations that interfere with other systems. They must survive the external environment. Once again, a solution becomes part of the larger geometry of the station. Now consider pressure. A slow leak begins. Perhaps the change is extremely small. The station's sensors detect a pressure trend. The crew may close hatches between sections to isolate the source. The station can become divided into smaller volumes. Measurements can help determine where pressure is being lost. The crew searches. The problem becomes detective work inside a spacecraft. This reveals another reason modules and hatches matter. A hatch is not only a passage. It can become a boundary. If one section develops a problem, closing hatches can help isolate it. Compartmentalization gives the station options. A completely open structure would offer fewer ways to contain a failure. Ships learned this lesson long ago. Submarines live by it. Space stations inherit it. A boundary can save the larger system. But boundaries create operational complexity. Hatches must work. Seals must remain healthy. Crew members must know which paths remain available. Emergency procedures must account for where people are. Visiting vehicles may serve as lifeboats. The station is therefore not only a habitat, it is a map of possible responses. Every hatch can be open in normal life, and closed when the station needs to become several smaller worlds. Now imagine smoke. Fire in microgravity does not behave exactly as familiar flames do on Earth. Buoyancy no longer pulls hot combustion products upward in the same way. Ventilation affects how gases and smoke move. The station must detect signs of fire and respond within a closed atmosphere where combustion products cannot simply escape through an open window. A fire threatens more than the object burning. It threatens the shared air, smoke, toxic gases, heat, damage to wiring, damage to structure, damage to equipment. And because airflow is essential for normal life, the same ventilation network that keeps air moving must also be considered during a fire response. The station systems are never isolated from context. A fan can be beneficial in one condition and require careful management in another. This is why procedures matter. The machine alone is not enough. People must know how to change the machine's behavior. Now imagine something smaller, a floating droplet of water. On Earth, a leak drips downward. The direction of the evidence is obvious. In microgravity, water may cling to surfaces, form spheres, travel along cables, hide behind panels. A small leak can become difficult to locate. Liquids near electronics are undesirable. So even the behavior of a leak changes when gravity no longer provides a preferred direction. The station's problems are often familiar problems with one familiar assumption removed: air without rising, water without falling, flames without ordinary buoyancy, bodies without weight bearing, objects without a resting place, heat without outdoor air, a building without ground. And this is why understanding a space station requires more than listing its components. The components exist because ordinary physical processes no longer organize the environment in the way humans evolved to expect. The station must create organization. Fans organize air, pumps organize fluids, handrails organize movement, straps organize bodies, containers organize objects, sensors organize information, procedures organize response, docking systems organize arrivals, attitude control organizes orientation, orbital maneuvers organize the station's path. Nothing up here happens by itself. The problem in full is disorder, not complete chaos. Just the constant tendency of a complex closed system to drift away from the conditions people need. Carbon dioxide rises, filters load, parts wear, orbits decay, bodies lose bone and muscle without sufficient loading, heat accumulates, waste accumulates, supplies decline, equipment ages. The station must continuously push back. This is why it never truly becomes finished. A building on Earth may be completed. A station in orbit is always being maintained, upgraded, repaired, reconfigured, resupplied, inspected. Its finished state lasts approximately until the next maintenance task. And perhaps that is the most honest answer to how space stations work. They work through continuous correction. Not one grand solution. Thousands of small corrections. A pump turns because fluid must move. A heater activates because a component is becoming too cold. A radiator rejects heat because equipment has become warm. A control system adjusts orientation. A visiting spacecraft provides supplies. An astronaut cleans a filter. A ground team notices a trend. A spare part replaces a warm one. The station survives through attention distributed across people and machines. The enemy is not simply vacuum. Vacuum is predictable. The enemy is not simply gravity. Gravity is predictable too. The harder enemies are subtler. Heat, wear, contamination, radiation, orbital debris, material fatigue, limited resources, human error, sensor uncertainty, the slow accumulation of tiny deviations. A space station is surrounded by spectacular scenery, but it is threatened most often by ordinary physics. A clogged filter does not look cinematic. A failing pump does not resemble a meteor storm. A rising carbon dioxide reading is just a number on a screen. Yet these quiet things matter. The station's greatest challenges often arrive without drama, and that brings us toward the forces working against every solution. The enemies that cannot be permanently defeated, only managed. Heat will continue to be produced, radiation will continue to arrive, materials will continue to age, the thin upper atmosphere will continue to create drag, tiny objects will continue moving through orbital space at enormous relative speeds, human bodies will continue responding to microgravity, machines will continue wearing out. The station does not win once, it wins temporarily, again and again, through correction. Our sleeping astronaut is still there, still breathing, the fan is still turning, but now we can hear what lies behind that simple sound. A whole station refusing, quietly, to drift away from habitability. The problem is fully visible now, so we can finally meet the forces that keep creating it. Let's go find them. The station has no single enemy. That would almost be easier. One enemy can be watched, named, studied, perhaps avoided. But a space station lives inside several environments at once. It lives inside vacuum, inside Earth's gravitational field, inside a stream of sunlight, inside a changing field of radiation, inside the outermost traces of Earth's atmosphere, inside a region crossed by natural particles and human-made debris, and inside itself, it lives with people, machines, moisture, heat, dust, waste, movement, wear. The enemies of a space station are therefore not villains, they are conditions. Most of them are perfectly ordinary pieces of physics. They are not angry, they are not trying to enter, they are not trying to damage anything. They simply continue behaving according to their own rules. The station survives by respecting those rules. Nothing up here happens by itself, and nothing stays perfect by itself. Let us begin with something that seems almost too small to matter. A particle. Perhaps a tiny fragment of metal. Perhaps a piece of material released during some earlier event in orbit. perhaps a natural micrometeoroid traveling through space. From a distance, it may be nearly invisible. On Earth, a tiny particle striking a building would usually be unimportant, but speed changes the meaning of size. Objects in orbit can encounter one another at extremely high relative velocities. At those speeds, even small particles can carry enough energy to damage spacecraft surfaces. This creates one of the strangest architectural problems in space station design. How do you build a wall against something too small to reliably track? Moving too quickly for the wall to simply be made thicker without an enormous mass penalty? The answer is not always one thick barrier. Often, it is distance. A type of protection commonly associated with spacecraft uses layers separated by space. An outer layer receives the initial impact. The incoming particle may break apart. The outer layer may also produce fragments. The impact becomes a spreading cloud of smaller material. A second layer, positioned behind the first, then receives a more dispersed impact. The goal is not to make the first layer invincible. The goal is to change the problem before the problem reaches the pressure vessel. This is an elegant idea. The shield sacrifices simplicity. It uses separation. The first encounter transforms the projectile. The gap gives the resulting debris cloud room to spread. The layers behind absorb and distribute what remains. Different parts of a space station can use different shielding arrangements depending on their geometry, expected exposure, and acceptable mass. The principle is more subtle than simply adding armor. The station cannot become a solid metal fortress. Mass remains a constraint, so protection must be intelligent. A small object may be too small to track from the ground. A larger object may be tracked. If a known piece of debris is predicted to pass too close to the station, the response can be entirely different. Instead of asking the wall to stop it, the station can move. This is one of the quiet advantages of living inside a spacecraft rather than a building. A building cannot dodge. A space station sometimes can. Orbital tracking networks observe objects around Earth. Predictions are made. Possible close approaches are evaluated. When necessary and possible, the station's orbit can be adjusted to reduce collision risk. The maneuver may be modest. In orbital mechanics, modest changes made at the correct time can create useful separation later. The station does not need to flee across the sky. It needs to make the future meeting fail to happen. This is an important pattern. Small debris is managed partly through shielding. Trackable debris can sometimes be managed through avoidance. Different sizes create different solutions. There is no single shield against the entire environment. And even when no collision occurs, the outside of the station is still being changed. Low Earth orbit is not truly empty. The station travels through extremely thin traces of Earth's upper atmosphere. The density is tiny compared with the air at the surface, but the station moves through it at orbital speed. Over time, even this thin atmosphere matters. It creates drag. The station loses orbital energy. Its altitude can gradually decrease, so the orbit must sometimes be raised. Reboost maneuvers restore altitude. Visiting spacecraft or station propulsion capabilities can contribute to this work. Again, the enemy is not dramatic. A trace of atmosphere, almost nothing. But almost nothing, repeated continuously, becomes something. This may be one of the deepest lessons of a space station. Small effects become large when given enough time. A tiny drag force matters across thousands of orbits. A small leak matters if it continues. A slightly loaded filter matters if it keeps collecting material. A small imbalance matters if it accumulates. A little bone loss matters across months. A small temperature change matters if sensitive equipment cannot tolerate it. The station is a machine built to notice accumulation. It watches trends. Because the first sign of a problem may not be a sudden event. It may be a line on a graph slowly leaning in the wrong direction. The atmosphere outside creates another unusual challenge. Atomic oxygen. At the altitudes of low Earth orbit, ultraviolet radiation from the sun can break ordinary oxygen molecules apart, producing highly reactive individual oxygen atoms. A spacecraft moving rapidly through this environment repeatedly encounters them. Some materials can erode. Polymers and coatings may degrade if they are not selected or protected appropriately. A surface that looks perfectly durable on Earth may behave differently after long exposure to vacuum, ultraviolet radiation, temperature cycling, and atomic oxygen. This is why spacecraft materials are tested for the environment they will actually inhabit. A material does not merely need to be strong, it may need to resist erosion, outgassing, radiation, vacuum, repeated heating and cooling, and years of exposure. The outside of a station is a laboratory in patience. Nothing needs to destroy a material in one dramatic moment. The environment can simply keep touching it, orbit after orbit, day after day, year after year. The sun rises, the sun sets. Although from the station, those words happen with unusual frequency. As the station circles Earth, it repeatedly moves between sunlight and Earth's shadow. External surfaces experience changing thermal conditions. A component exposed to direct sunlight may warm. Then the station enters darkness. Conditions change again. Materials expand when heated, contract when cooled. Repeated thermal cycling can stress structures and connections over long periods. So temperature is not merely about keeping astronauts comfortable. It is a structural and mechanical concern. Different materials expand by different amounts. Electronics have operating limits. Batteries have preferred conditions. Fluids must remain within usable temperature ranges. Some external equipment may need heaters to avoid becoming too cold. Other equipment must be cooled. The station is not simply hot or cold, it contains many thermal environments at once. Sunlight may strike one side, a radiator may face deep space, equipment inside may generate heat, a shadow may move across an external structure. The thermal control system must manage this shifting landscape, and unlike a house, the station cannot solve the problem by opening a window. Now we return to the human body, because one of the station's most persistent enemies is also the condition that makes floating possible. Microgravity. The astronaut experiences weightlessness. Objects drift. Movement can look effortless. A gentle push sends a person across a module. For a visitor watching video from Earth, it may appear playful. And often it is. But the human body was shaped by gravity. Bones respond to loading. Muscles respond to use. The cardiovascular system has spent an entire lifetime working within a gravitational field. Remove the usual mechanical demands, and the body adapts. That word is important. The body is not simply breaking, it is adapting to a new environment. The difficulty is that the astronaut eventually intends to return to an environment where gravity matters again. In microgravity, bones that normally bear weight receive less loading. Without effective countermeasures, bone density can decrease. Muscles that usually work to support posture and movement can weaken. The body becomes efficient for the environment it currently inhabits. Unfortunately, Earth is waiting, so exercise aboard a space station is not simply recreation, it is part of life support. This is a remarkable expansion of what life support means. We began with air, then water, then pressure. But a station can provide perfect oxygen and still fail to preserve the human body for return to gravity. The habitat must support physiology. Astronauts therefore exercise regularly using specialized equipment. A treadmill allows running while restraints hold the body toward the moving surface. A stationary bicycle provides cardiovascular exercise without requiring the rider to balance on a road. A resistive exercise device allows movements that can load muscles and bones without relying on ordinary weights. Because an ordinary barbell has a problem in microgravity. Its mass remains, its inertia remains, but its weight largely disappears in the familiar sense. A heavy object no longer presses downwards simply because it is heavy. So exercise equipment must create resistance in other ways. The station must manufacture effort. On Earth, gravity provides resistance for free. In orbit, nothing up here happens by itself. Even exercise must be engineered, and the body faces another change. Fluids shift. On Earth, gravity helps pull body fluids toward the lower parts of the body. In microgravity, that familiar distribution changes. Fluids move toward the upper body and head. Astronauts may initially experience a puffy face and a sense of congestion. Over longer missions, researchers have studied changes involving the eyes and vision. The body is again adapting. The problem is not that the human organism has forgotten how to work. The problem is that it is working under different rules. This makes the astronaut both resident and experiment. Every long-duration crew helps researchers understand how humans respond to spaceflight. Measurements before flight, during flight, after flight, blood, vision, bone, muscle, balance, sleep, immune function, microorganisms. The station studies the people who operate the station, a laboratory examining its own inhabitants, and those inhabitants bring another enemy with them: time. Human beings become tired. Attention changes. Sleep can be disturbed. Workloads can become demanding. Isolation matters. Noise matters. Schedules matter. The station may circle Earth rapidly, but the human brain still needs a daily rhythm. Light and darkness outside do not provide the same simple pattern as a terrestrial day. The station can experience many sunrises and sunsets, while Earth below completes one ordinary day, so crew schedules and lighting help support human routines. Sleep remains essential, and our sleeping astronaut returns again. Why does a space station need fans to keep a sleeping astronaut alive? Because sleep does not pause the engineering. The astronaut may stop working. The station cannot. While the person sleeps, carbon dioxide is still produced, heat is still produced, water vapor is still released. The body still needs oxygen. The cabin still needs circulation. The atmosphere still needs cleaning. The station still needs power. The orbit continues. The cooling loops continue. Computers continue watching. Ground teams continue monitoring. The sleeping astronaut has surrendered conscious control. For several hours, the station must become trustworthy enough to be ignored. That may be one of the highest standards any machine can meet. Not merely functioning while someone watches it, functioning while someone sleeps inside it. But the body and the outside environment are not the only enemies. There is radiation. Earth provides substantial protection to people on the ground. The atmosphere and magnetic environment reduce exposure to many forms of space radiation. A station in low Earth orbit still benefits from Earth's magnetic field, compared with deep space. But the radiation environment is different from the surface. Energetic particles can pass through materials. Exposure accumulates. Shielding can help. Mission planning matters. Monitoring matters. But radiation presents a difficult mass problem. More shielding can provide more protection against some radiation environments. But shielding has mass. And as we already know, mass must be launched. This creates another trade. Protection versus weight. The answer is not simply to surround the station with an arbitrarily thick shell. Engineering rarely receives unlimited material. Instead, designers consider the environment, mission duration, spacecraft geometry, available materials, operational strategies, and acceptable risk. The station becomes a compromise shaped into metal. Radiation also reminds us that not every threat can be seen. An astronaut can look through a window and see Earth, clouds, ocean, nighttime cities, lightning, auroras. None of that reveals the invisible particles passing through the surrounding environment. A space station depends on instruments partly because human senses evolved for Earth. We cannot see carbon dioxide, we cannot see pressure, we cannot see most radiation, we cannot see a microscopic crack hidden behind a panel. We cannot hear orbital drag, we cannot smell a failing bearing through a sealed machine before it produces any detectable symptom. So the station extends perception through sensors, temperature sensors, pressure sensors, gas monitors, smoke detection, electrical measurements, vibration data, cameras, medical measurements. The machine becomes aware of itself through numbers, but sensors introduce another enemy: uncertainty. A measurement can be wrong, a sensor can drift, a reading can be noisy, a cable can fail, a computer can misinterpret data. This means the station cannot merely measure. It must compare, confirm, cross-check. Sometimes the question is not what is happening, it is, can we trust the instrument telling us what is happening? This is a quieter kind of danger. The difference between a real failure and a faulty indication. Engineers and controllers look for patterns. Does another sensor agree? Did another measurement change at the same time? Does the crew observe anything unusual? Can the system be tested? Can the reading be reproduced? The station is partly a machine for distinguishing reality from measurement, and then there is where. A bearing rotates, a pump operates, a valve cycles, a seal is compressed, a filter collects particles, a connector is used, a cable is flexed, a treadmill receives repeated loads, a toilet processes waste, a fan turns, again and again and again. Reliability is not the absence of use, it is the ability to survive use for long enough, and to be repaired when survival ends. This is why maintenance is not an interruption to station life. Maintenance is station life. The station is inhabited by people who are also caretakers of the habitat. They clean, inspect, replace, lubricate, troubleshoot, photograph, measure, report. Sometimes a repair is planned for months. Sometimes an unexpected problem changes the day's schedule. Sometimes a component is replaced with a spare. Sometimes a workaround allows the station to continue without the original capability. Sometimes a part designed on Earth is launched later. The station's history is written partly in repairs, and this is important because the International Space Station has operated for far longer than many individual consumer machines ever do. Its systems have been used continuously. Hardware has aged, new hardware has arrived, old equipment has been replaced, software has changed. Experiments have come and gone. Vehicles from different programs have visited. The station is not frozen in the year it began. It has evolved while inhabited. This makes age another enemy, but also a source of knowledge. A new spacecraft design can be tested for years before flight, but only long operation reveals what long operation actually feels like. Which parts become troublesome, which procedures take too long, which filters need more attention than expected, which components are difficult to access, which spare parts are used, which noises bother crews, which surfaces collect contamination, which systems are robust, which systems are temperamental. Time reveals design. The station has spent years answering questions that cannot be fully answered in a laboratory on Earth. And perhaps the most interesting enemy is complexity itself. A station needs complexity to survive. It needs life support, power, thermal control, communications, guidance, navigation, attitude control, docking, computers, fire detection, exercise equipment, waste management, scientific facilities, robotic systems. Each capability solves a problem, but each capability introduces hardware, software, interfaces, maintenance, failure modes. The station must therefore become complex without becoming incomprehensible. This is why systems are divided, why procedures exist, why labels matter, why training takes years, why ground teams specialize. No single person needs to hold every detail of the entire station in their mind at once. Knowledge is distributed. One specialist understands a particular system deeply, another watches a different system. Crew members are trained across many areas. Computers handle rapid monitoring and control. Documentation preserves procedures. The station works because intelligence is spread across a network of people and machines. In orbit, on Earth, across countries, across control centers, across shifts. A person can go to sleep because someone else remains awake. And even when the human watchers change, the systems continue. This gives us a different answer to our central question. Why does a space station need fans to keep a sleeping astronaut alive? Because the enemy is not merely carbon dioxide. The enemy is separation. The separation between a person's lungs and the machine that can clean the air. The fan closes that gap. It moves the waste gas toward the equipment designed to remove it. And this pattern appears everywhere. A pump closes the gap between heat and a radiator. A cable closes the gap between a solar array and an electrical load. A docking system closes the gap between a visiting spacecraft and the station. A communication link closes the gap between orbit and the ground. An exercise machine closes the gap between microgravity and the mechanical loading the body needs. A shield closes part of the gap between a tiny projectile and a pressure vessel. A procedure closes the gap between a failure and a response. The station is made of connections. The enemies create separation, distance, isolation, accumulation. Where? The station answers with loops. Move the air, move the water, move the heat, move the electricity, move the information, move the station itself when necessary. Nothing up here happens by itself. But this phase has left us with a problem. If the enemies never disappear, how can the station ever win? The answer is that it does not try to eliminate them. It does something more elegant. It turns continuous problems into continuous processes. Carbon dioxide is continuously produced, so remove it continuously. Heat is continuously produced, so transport and reject it continuously. The orbit is continuously affected, so monitor and adjust it. The body continuously adapts to microgravity, so exercise continuously. Equipment continuously ages, so inspect and maintain it. The station does not seek a final victory. It seeks balance, dynamic balance, a condition that exists only because something keeps maintaining it. And now, we are ready for the elegant solution, not one machine, not one invention. A philosophy of engineering hidden inside thousands of parts. The solution is circulation, loops, cycles, feedback. The station survives by taking things that would otherwise accumulate and making them move. Let's go find it. Imagine trying to build a space station with no loops. Air enters, then leaves, water arrives, then becomes waste. Electricity is stored once, then disappears. Heat accumulates, carbon dioxide accumulates, waste accumulates. Every useful resource moves in one direction, from supply to consumption to loss. Such a station could exist for a while. A short mission can carry consumables. A capsule can begin with stored resources and return before those resources run out. But a long-duration station asks for something different. It asks for repetition. A day, then another day, then another, a month, a year, years of continuous human presence. The elegant solution is not to carry an impossibly large pile of everything. It is to make resources travel in circles whenever possible. The circle does not have to be perfect. It only has to reduce loss enough to make continued operation practical. This is the hidden beauty of a space station. From the outside, its most recognizable features are enormous solar arrays and a long structure. From the inside, its deepest architecture is circular. Air circulates, water circulates, cooling fluid circulates. Electrical energy follows networks. Information travels in feedback loops. The station orbits. Crew schedules repeat. Maintenance cycles repeat. Visiting vehicles arrive and depart. The entire machine is built around return. Something leaves, changes, and comes back useful. Nothing up here happens by itself, so the station creates motion. Let us begin where we began, with air. A fan turns. Cabin air enters a ventilation system. The movement helps prevent stagnant regions. It distributes heat. It carries carbon dioxide toward removal equipment. It carries humidity towards systems that can condense and recover water. It helps move trace contaminants toward filtration and cleanup systems. The air returns, not as entirely new air, as managed air. That distinction is the elegance. The station does not need to replace every molecule after every breath. It needs to keep the mixture within acceptable conditions. Oxygen consumed by the crew must be replenished. Carbon dioxide must be removed. Contaminants must be controlled. Humidity must be managed. Pressure must remain suitable. The atmosphere becomes a maintained composition, a recipe that is continuously being disturbed and continuously corrected. The same logic appears in water. Water enters the crew. Some leaves through urine, some through sweat, some through breath, some becomes humidity. The station tries to recover part of that water. Wastewater is processed. Moisture is collected. Purification equipment removes unwanted substances. The recovered water can return to use. Again, not perfect closure, but a loop. The more effective the loop, the less water must arrive from Earth. Now consider oxygen. Water can be used as a source. Electrical energy can split water into oxygen and hydrogen. The oxygen supports the cabin atmosphere. The hydrogen can participate in another process. Carbon dioxide removed from the cabin can react with hydrogen. Water can be produced and recovered. Part of what began as exhaled carbon dioxide returns toward the water system. The chemistry is more complicated than a simple circle drawn on paper. There are losses, waste products, maintenance needs, energy costs, but the direction is clear. The station is trying to stop useful atoms from leaving. This is the elegant solution to scarcity. Do not ask only, how much do we have? Ask, how many times can we use it? A kilogram of water used once is 1 kilogram of useful water. A kilogram recovered and reused repeatedly becomes far more valuable over time. The same physical matter supports many days of life. The station stretches resources through repetition. Now follow heat. Inside the cabin, people and machines produce thermal energy. Air can carry some of that heat toward heat exchangers. Water loops can collect heat from internal systems. The heat is transferred through the station. External cooling loops can carry it toward radiators. The radiators emit thermal energy into space. The fluid returns cooler, then collects more heat. Another loop. The radiator is not a container where heat is stored. It is a place where heat leaves the station. The cooling fluid is the courier. It travels, collects, delivers, returns. This is why pumps matter so much. A pump creates circulation where gravity cannot be trusted to create it. On Earth, natural convection can move warm fluids in useful ways. In microgravity, designers cannot simply assume that warm fluid will rise and cool fluid will fall. The system must impose direction. The pump tells the fluid where to go. The fan tells the air where to go. The station replaces natural tendencies with controlled circulation. And once again, our sleeping astronaut is connected to the radiator outside. The connection is not obvious, but it is real. The astronaut produces heat. The air around the body warms. Ventilation moves that air. Heat exchangers and cooling systems help manage the cabin temperature. Thermal energy enters circulating fluids. Eventually, external radiators help release energy into space. A warm sleeping human, and a large panel outside the station are parts of the same thermal story. Everything touches something else. Now follow electricity. Solar arrays convert sunlight into electrical energy. That energy is distributed through the station. Some powers equipment immediately. Some supports energy storage for periods when sunlight is unavailable. As the station moves into Earth's shadow, the solar arrays no longer receive direct sunlight. The station does not turn off. Stored energy supports continued operation. Then sunlight returns. The cycle changes again. Generation, storage, use, recharge, orbit after orbit. The station's electrical system is another answer to periodic scarcity. Sunlight is not continuously available to the arrays during every part of every orbit. So the station separates. The time energy is collected from the time energy is needed. Batteries make sunlight portable through darkness. This is one of the quiet powers of energy storage. It moves energy through time. A solar array collects energy earlier. A battery makes some of that energy available later. The station crosses into shadow, and the fans continue turning. The sleeping astronaut may never notice. This is what good infrastructure does. It hides transitions. Sunlight becomes darkness. Power generation changes. The cabin remains habitable. A person keeps breathing. Nothing up here happens by itself. But when the system works well, it can feel that way. Now consider orientation. The station is not a passive object tumbling randomly through orbit. Its attitude, its orientation in space, matters. Solar arrays need useful exposure to sunlight. Radiators need suitable geometry for thermal control. Docking operations require predictable orientation. Communications and experiments may have pointing needs. The station's large structure experiences environmental torques, so attitude must be managed. One elegant tool for this is the control moment gyroscope. Instead of using propellant for every routine adjustment in orientation, large spinning devices can exchange angular momentum with the station. By changing the orientation of spinning rotors, the system can produce torque on the station. The result is almost philosophical. The station changes its orientation by rearranging motion already stored inside itself. No atmosphere to push against. No need to imagine a rudder in empty space. Momentum is exchanged within the system. The station turns. The gyroscopes take on the corresponding change in angular momentum. But even this elegant solution has a limit. The gyroscopes can accumulate momentum from persistent external disturbances. Eventually, they may approach conditions where they cannot continue absorbing more in the required direction. Then the stored momentum must be managed. Thrusters can help unload the system. Another loop, another correction. Another reminder that no elegant solution eliminates physics, it simply works with it. The station uses propellant when propellant is useful. It uses momentum exchange when that is more efficient. Different tools for different scales of correction. This is the pattern again. There is rarely one universal answer. The elegant system is the one that chooses among answers. Now consider orbit itself. The station is continuously falling around Earth. The thin atmosphere creates drag. Over time, the orbit can lose altitude, so the station receives reboosts. Propulsion changes its velocity. A relatively small change in velocity can alter the orbit. The station is raised, then drag begins its patient work again. The orbit is not a fixed rail, it is a condition maintained through motion. The station remains in space because it is moving fast enough sideways. It remains within its operational altitude range because that orbit is monitored and adjusted. Another dynamic balance. The elegant solution to orbit is not stillness, it is controlled falling. The elegant solution to atmosphere is not sealing one perfect batch of air forever. It is continuous processing. The elegant solution to water is not carrying an ocean, it is recovery. The elegant solution to heat is not preventing heat from being produced, it is transport and radiation. The elegant solution to human deconditioning is not recreating Earth's gravity throughout the station. It is targeted exercise. The elegant solution to every possible failure is not making failure impossible. It is detection, redundancy, repair, adaptation. This is why a space station is more than hardware. It is a set of feedback loops. A sensor measures, a controller compares, a machine responds. The environment changes. The sensor measures again. Consider cabin temperature. If the temperature drifts, the thermal system responds. Consider pressure. If pressure changes unexpectedly, the station monitors the trend and the crew can investigate. Consider carbon dioxide. Measurements reveal whether removal systems are maintaining acceptable conditions. Consider electrical power. Generation and demand are balanced. Consider orientation. Sensors determine attitude. Control systems respond. The station is constantly asking, where am I now? Where should I be? What difference exists between those two states? What action reduces the difference? That is feedback, and feedback may be the most important invisible technology aboard any complex spacecraft. Without feedback, a machine acts blindly. With feedback, it can correct. The station is never perfectly motionless, perfectly constant, perfectly clean, perfectly balanced. It does not need to be. It needs to remain within acceptable ranges. This is another elegant idea. Engineering does not demand perfection where tolerance will do. A cabin temperature can vary within a range. Pressure can be controlled within limits. An orbit can change while remaining useful. A machine can age while remaining functional. A human body can adapt while countermeasures reduce harmful effects. The station survives inside envelopes, boundaries, margins, acceptable regions. This makes the station less like a statue and more like a living process, not alive, but continuously regulated. A heartbeat is not a fixed state, it is repetition. Breathing is repetition. Body temperature is maintained through feedback. Water balance is regulated. The station uses a similar logic. Measure, respond, repeat. The resemblance is not accidental. Any habitat supporting humans for long periods must manage flows. The human body does it biologically, the station does it mechanically, and the two systems connect. The astronaut breathes, the station processes the atmosphere. The astronaut drinks. The station recovers water. The astronaut produces heat. The station rejects heat. The astronaut exercises. The station provides resistance. The astronaut sleeps. The station remains awake. Why does a space station need fans to keep a sleeping astronaut alive? Because the fan is part of a loop. The astronaut's lungs are not separate from the station. For the duration of the mission, they are connected to it. The lungs exchange gases with the cabin. The cabin exchanges gases with life support equipment. The life support equipment depends on power. The power system depends on solar energy and storage. The equipment creates heat. The thermal system moves that heat. The station controls its orientation. Its orbit is maintained. Ground teams support operations. Visiting vehicles bring supplies. A single breath reaches outward through an enormous web of engineering. And then, the web returns to the next breath. This is the elegant solution. Not independence, interdependence. Every system supports another. The station survives not because each part can live alone, but because the parts exchange what they have. Airflow delivers gas to a scrubber. A scrubber protects the atmosphere. Water processing supports oxygen generation. Power supports the processors. Cooling supports the power electronics. Attitude control supports the geometry of the vehicle. Propulsion supports orbit and momentum management. Communications support human decisions. Maintenance supports everything. A station is a conversation among machines. One machine says, "I have heat." Another says, "Bring it here." One says, "I have carbon dioxide." Another says, "I can separate it." One says, "I need electricity." Another says, "Sunlight has returned." One says, "My filter is becoming loaded." A sensor says, "Someone should know." The crew responds, the loop closes. Nothing up here happens by itself, but almost nothing happens alone. And now that we understand the loops, we can slow down even further, because saying that water is recycled is easy. Saying that heat is moved is easy. Saying that air is cleaned is easy. The real machinery lives in the sequence. What happens first? What happens next? Where does the material go? How does one process become the input for another? How does a breath become a measurement, a captured gas, a chemical feedstock, water, and perhaps oxygen again? The elegant solution has shown us the shape. Now we need to follow the cascade, step by quiet step. Let's begin. A breath leaves the astronaut. Let us follow it. Not quickly. There is no need. The gas is warm, moist, rich in carbon dioxide compared with the air that entered the lungs only moments earlier. It leaves the mouth or nose and enters the cabin. On Earth, buoyancy would help shape what happens next. Warm air tends to rise. Cooler air tends to fall. Convection helps stir the atmosphere. But aboard the station, the familiar upward path is missing. The breath does not receive a simple instruction from gravity. So the station provides one. A fan turns. The moving cabin air catches the exhaled gas. The breath begins to lose its identity. It mixes with the larger atmosphere. Molecules that were together inside one person's lungs spread into the shared cabin. The carbon dioxide becomes part of the station's atmospheric load. The water vapor becomes part of its humidity. The heat becomes part of its thermal load. One breath has already become 3 engineering problems: gas composition, moisture, heat, and the station handles each through a different path. This is the cascade. One event enters the habitat. Several systems respond. Nothing up here happens by itself. The atmosphere moves through the cabin. Ventilation grills and ducts help guide circulation. The goal is not simply to create a pleasant breeze. The goal is to make the atmosphere available to the equipment that manages it. The carbon dioxide must reach carbon dioxide removal equipment. Humidity must reach surfaces or systems that can remove moisture. Heat must reach thermal control equipment. Trace contaminants must reach filtration systems. The air becomes a transport network. The fan is the first courier. Now the carbon dioxide reaches a removal system. The precise machinery used aboard a station can vary. Different systems can operate at different times. New technologies can be tested. Equipment can be upgraded. But the basic task remains. separate carbon dioxide from the useful cabin atmosphere. A material inside the removal equipment selectively captures carbon dioxide under one set of conditions. Cabin air passes through. The unwanted gas is retained. The remaining air continues. But the capture material cannot collect forever. Eventually, it must release what it has captured. So the system changes conditions. The carbon dioxide is driven off. The material is regenerated. Then it can capture again. Collect, release, collect, release. The machine breathes in its own mechanical way, not oxygen in and carbon dioxide out, but carbon dioxide in, then carbon dioxide concentrated elsewhere. This is an important step. The station has taken a diffuse problem and concentrated it. Before removal, carbon dioxide was mixed throughout the cabin atmosphere. After separation, it exists as a more manageable stream. Concentration makes the next step possible. Some carbon dioxide may ultimately be discarded, but part can enter a recovery process. Now we need another substance, hydrogen. Where does it come from? Water. The station can use electrical energy to split water. The process produces oxygen and hydrogen. The oxygen is useful to the crew. It can enter the cabin atmosphere. Eventually, a person breathes it. The hydrogen takes another path. Hydrogen can be combined with carbon dioxide in a chemical process. The reaction produces water and methane. The water can be recovered. The methane represents material that is more difficult to close into the existing loop and may be discarded. So the cycle is incomplete, but it is tighter than before. Let us follow the oxygen first. Water enters the oxygen generation equipment. Electricity drives the process. Oxygen emerges. The oxygen enters the station's atmosphere. Ventilation distributes it. The sleeping astronaut inhales. The oxygen travels into the lungs, across delicate biological membranes, into the blood, through the body. The body's cells use oxygen as part of the chemistry that releases usable energy from food. Carbon dioxide is produced. The blood carries it back toward the lungs. The astronaut exhales, and we are where we began. A breath leaves the astronaut. The loop has returned, not perfectly, not with the same individual molecules necessarily following one neat path. Real systems mix, flows combine, materials are stored, processes operate according to demand and availability, but the overall cycle is clear. Water helps provide oxygen. The astronaut uses oxygen. Carbon dioxide is produced. The station removes carbon dioxide. Some of that carbon dioxide participates in a process that recovers water. The water can return. This is the cascade of breath, and it depends on electricity. So now, we follow the power. Outside the station, sunlight reaches the solar arrays. Photovoltaic cells convert part of the incoming solar energy into electrical energy. The arrays are large because the station has large demands. Life support, computers, experiments, lighting, pumps, fans, communications, exercise equipment, heaters, scientific instruments, robotic systems. The station is an electrical city with very few citizens. The energy collected outside enters the station's electrical system. It is conditioned, managed, distributed. Some is used immediately, some is stored. Then the station moves into Earth's shadow. Direct sunlight disappears from the arrays. But the fan must continue. The carbon dioxide removal equipment must continue as required. Computers must continue. Thermal control must continue. The station cannot become uninhabitable every time Earth blocks the sun, so stored electrical energy takes over. The transition is managed. The station crosses darkness. Then sunlight returns. The arrays generate again. Energy storage is replenished. The cycle repeats. Sunlight, shadow, sunlight, shadow. The station moves through this rhythm many times while a person on the ground experiences one ordinary day. And every time, the electrical system follows. Now consider what happens after the electricity is used. Suppose electrical energy powers a fan. The motor turns, the blades move air, the fan performs useful work, but not all the energy disappears into usefulness. Eventually, much of it becomes heat. The motor warms. Electrical resistance creates heat. Moving machinery creates heat. The air receives heat. The station has solved the airflow problem and added a little thermal energy to the cabin. This is not a flaw, it is physics. Almost every watt used inside the station eventually contributes to the heat that must be managed. A computer performs calculations, then becomes warm. A light produces illumination, then contributes heat. A person eats food. The body releases energy, then becomes part of the thermal load. The station is continuously converting useful energy into lower temperature heat. That heat must go somewhere, so now we follow the warmth. Inside the station, air circulation helps carry heat. Thermal control equipment collects it. Liquid cooling loops transport it. Water is useful as an internal heat transfer fluid because it can carry substantial thermal energy. But the station must eventually move that heat outside the pressurized modules. The internal and external thermal systems are separated for good reasons. Outside the station, the environment is vacuum. External cooling loops may use a different working fluid suited to their operating conditions. Heat exchangers allow thermal energy to cross from one loop to another without requiring the fluids themselves to mix. The heat moves. The fluids remain separate. This is another elegant boundary. Exchange the thing you want. Without exchanging everything, thermal energy crosses. Fluid does not. The external loop carries the heat toward radiators. The radiators expose large surfaces to space. Thermal energy leaves as infrared radiation. No breeze is required, no surrounding air. The energy departs as electromagnetic radiation. The cooling fluid returns, ready to collect more heat. The loop closes. A fan turns inside. A radiator glows invisibly outside. Between them lies a chain of energy transfer. The sleeping astronaut never sees it, but the warmth of that sleeping body is participating in the same cascade. Heat leaves the skin. The cabin air and surrounding surfaces receive it. Cooling systems collect part of the thermal load. Fluid carries energy, radiators release it. The body remains within a comfortable environment because the station has built a path from human warmth to empty space. Nothing up here happens by itself. Now follow the water. The astronaut drinks. Some water becomes part of the blood. Some participates in cellular processes. Some helps regulate temperature. Eventually, water leaves the body through urine, through sweat, through breath, through ordinary biological processes that continue whether the astronaut is thinking about them or not. The water enters different parts of the station's recovery system. Humidity in the cabin air can be condensed. Wastewater can be collected. Urine enters dedicated processing equipment. Recovering water from urine in microgravity is not as simple as placing a container beneath it and waiting for gravity to separate liquid from vapor. The system must actively manage fluids. A urine processing system can use distillation under reduced pressure and mechanical techniques designed for the microgravity environment. The goal is to recover water while separating concentrated waste. The recovered water is not immediately assumed to be ready to drink. It enters further treatment. Water processing equipment removes contaminants. Filters and treatment stages help purify it. Sensors and testing help verify quality. The result returns to the station's usable water supply. The water may later be drunk, used in food preparation, or sent toward oxygen generation. A molecule that left a person as waste may return as drinking water, then become oxygen, then enter a lung. The categories are temporary: waste, resource, breath, water. The station keeps changing the labels. This is why the phrase recycled urine is both technically suggestive and conceptually incomplete. The station is not preserving urine, it is destroying the usefulness of that category. It is separating water from what should not remain in the water. Once purification is complete, the previous history of the molecule becomes chemically irrelevant. Water is water. the station is less sentimental than the human imagination, and more efficient. Now the cascade moves toward waste. Not everything can be recovered. Food packaging remains. Used materials accumulate. Worn equipment must sometimes be discarded. Concentrated waste from water recovery remains. Human waste that cannot be usefully processed aboard the station must be stored and eventually removed. Cargo vehicles become part of this system. A vehicle arrives carrying useful mass, food, experiments, equipment, spare parts, clothing, supplies. The cargo is transferred into the station. Over time, the vehicle can be filled with waste and unwanted material. For certain uncrewed cargo spacecraft, departure leads to destructive re-entry. The vehicle and its waste burn up in the atmosphere. This is not recycling, it is disposal, and it reveals an important truth. A space station does not need every loop to close. It needs enough loops to close. Some material can be discarded, some must be resupplied, some can be recovered. The engineering question is where recycling provides enough benefit to justify the machinery required. This is the cascade of resources. A cargo vehicle brings a replacement part. The part keeps a water processor operating. The water processor recovers water. The water supports oxygen generation. The oxygen supports the crew. The crew performs experiments. The experiments produce data. The data travel to Earth. The cargo vehicle later removes waste. One launch can participate in many chains. Now follow information. A sensor measures carbon dioxide. The measurement enters a computer system. The value can be displayed, recorded, transmitted, compared with expected conditions. If the reading changes, people can investigate. Perhaps the crew checks equipment. Perhaps ground controllers analyze trends. Perhaps another sensor is consulted. Perhaps the system configuration is changed. Information becomes action. Action changes the environment. The sensor measures again. This is a feedback cascade. Physical reality becomes data. Data become interpretation. Interpretation becomes a command. The command changes physical reality. Then reality becomes new data. The loop closes. The station depends on these loops because humans cannot directly sense many of the conditions that matter. A person cannot look at air and determine its carbon dioxide concentration, cannot feel the exact pressure trend of a slow leak, cannot see the state of charge inside a battery, cannot know the temperature inside every piece of equipment by touching the outside. Sensors translate the hidden station into something understandable. The station becomes legible. And this legibility extends to the ground. The International Space Station is not operated only by the people inside it. Teams on Earth support the mission. Specialists monitor systems. Scientists work with experiments. Flight controllers coordinate operations. Engineers investigate anomalies. Communication links carry voice, video, commands, telemetry, scientific data. The station is physically in orbit, but operationally connected to Earth. This connection creates another cascade. An astronaut notices an unusual sound. The observation is reported. Ground teams review data. Engineers compare the sound with system behavior. A procedure is developed. The crew performs an inspection. Images are sent down. A decision is made. A repair may follow. A small noise becomes a global chain of expertise. The station works because knowledge can move faster than hardware. A replacement part may take time to launch. Advice can arrive almost immediately. The crew carries tools. The ground carries enormous distributed memory. Together, they form the maintenance system. Now follow movement. An astronaut wants to cross a module. On Earth, walking depends on friction with the floor and gravity keeping the body in contact with it. In microgravity, walking becomes unnecessary. The astronaut pushes gently against a handrail. The body accelerates, then continues moving. To stop, another force is required. A hand reaches for another rail. The astronaut pulls. Motion changes. Newton's laws are not absent. They are more visible. Every push matters. A careless movement can send a body rotating. A loose object can drift. A tool released without restraint can continue traveling until it meets something. So the station provides handrails, foot restraints, tethers, attachment points. The architecture guides momentum. Even human movement becomes a controlled cascade. Push, drift, catch, stop, turn, push again. The body learns. Experienced astronauts become graceful. They stop trying to walk. They begin thinking in 3 dimensions. A destination may be above, below, behind, or simply across a volume where those words have become optional. This changes work. An astronaut can position the body at angles impossible to maintain comfortably on Earth. But the body must also be restrained when force is required. Turning a tool can rotate the person instead of the fastener if the body is not anchored. Exercise requires restraints. Sleeping bags are attached so the sleeper does not drift into equipment or ventilation paths. The station is full of places where motion must be given a reference. Now follow a meal. Food arrives from Earth. It has been selected and packaged for storage, preparation, nutrition, and use in microgravity. The astronaut opens a package. The food must remain manageable. Crumbs can float. Liquids behave differently. Surface tension becomes more noticeable when gravity no longer pulls the liquid into a flat surface at the bottom of a cup. A drink may be consumed from a sealed container. Utensils and packages may be attached to a surface. The meal enters the body. Nutrients become energy. Metabolism produces heat, water, carbon dioxide, waste, and once again, food enters the station's larger loops. The carbon atoms travel, the water travels, the packaging travels, the heat travels. Nothing simply ends. Every action has an output. Now follow exercise. The astronaut secures the body to a machine. A treadmill uses a restraint system to keep the person against the running surface. Without restraint, each step would push the runner away. A resistive exercise device creates forces that can load muscles and bones. The astronaut works. Heart rate rises. Breathing increases. More oxygen is consumed. More carbon dioxide is produced. More heat is produced. More water vapor enters the cabin. Exercise protects the body and increases the immediate load on life support. The station accepts this trade because preserving human health is part of the mission. One system works harder, so another system, the human system, can remain capable. Everything touches something else. Now follow a docking spacecraft. It begins far from the station. Its orbit must be carefully arranged. The spacecraft cannot simply point at the station and accelerate directly toward it. Both vehicles are moving rapidly around Earth. Their trajectories must be coordinated. The visiting spacecraft performs orbital maneuvers. It changes its path. Gradually, the geometry brings the vehicles together. Relative motion becomes the important motion. From Earth, both are traveling at orbital speed. From one vehicle to the other, the final approach can be slow and controlled. Sensors help determine position and relative velocity. The spacecraft approaches a docking or berthing interface. Alignment matters. Contact occurs. Mechanical systems capture and secure the connection. The interface becomes structurally joined. Seals help establish a pressure-tight connection. Checks are performed. Only when conditions are correct can hatches eventually open. Two spacecraft become one connected, pressurized environment. A new volume joins the station. New people may enter, new cargo, new experiments. The station's mass changes, its configuration changes, its inventory changes, its future changes. Docking is not merely parking. It is the temporary merging of two life support worlds, and when the vehicle leaves, the process reverses. Hatches close. The pressure boundary is confirmed. Mechanical connections release. The vehicle separates. The station becomes itself again. Although not exactly the same self, it may have more supplies, less waste, a different crew, new hardware, a changed mass distribution. The station evolves through arrivals. Now follow orientation. The station experiences small talks, from environmental effects and operations. Its desired attitude must be maintained. Sensors determine orientation. Control systems compare the actual attitude with the desired one. Control moment gyroscopes can apply torque without continuously consuming propellant for routine attitude control. The station responds, but the gyroscopes themselves accumulate angular momentum. Eventually, external torque or thruster assistance may be used to unload that momentum. Again, a cascade. Disturbance, detection, correction, accumulation, reset, return. The station does not remain oriented because it was pointed correctly once. It remains oriented because the process of correction continues. The same is true of orbit. Drag acts. Altitude changes gradually. Tracking reveals the orbital state. A reboost is planned. Propulsion changes velocity. The orbit changes. Then drag continues. No final correction exists, only the next one. This may sound exhausting, but the station does not experience it as exhaustion. A machine does not resent repetition. The pump turns, the fan turns, the station orbits, the computer checks, the radiator radiates. The cycle is the work, and perhaps this is why space stations can feel strangely calming when understood closely. They are not surviving through one heroic act. They are surviving through routine. 1,000 ordinary processes, repeated correctly. A fan moving air, a pump moving fluid, a filter capturing contaminants, a battery charging, a sensor measuring, a controller adjusting, a person exercising, a crew member replacing a component, a cargo vehicle arriving, a radiator releasing heat. No single moment contains the entire station. The station exists in the repetition. Nothing up here happens by itself. But once the loops are established, one process can support the next. The cascade becomes continuity. Now return to the sleeping astronaut. The eyes are closed. The sleeping bag is attached. The body produces heat. The lungs consume oxygen. Carbon dioxide leaves with each exhalation. Water vapor enters the cabin. The fan moves the air. The carbon dioxide removal system processes the atmosphere. The oxygen supply is maintained. The water recovery system collects moisture. The power system keeps the machinery operating. The thermal system carries away heat. The radiators release energy. The attitude control system maintains orientation. The station continues around Earth. Ground teams watch. Sensors measure. Computers compare. The astronaut sleeps through the cascade. Why does a space station need fans to keep a sleeping astronaut alive? Because there is no single machine keeping the astronaut alive. The fan is the entrance to a chain, and every link matters. Airflow, removal, recovery, power, cooling, control, monitoring, maintenance. A breath is never only a breath inside a closed habitat. It is an input, an output, a chemical event, a thermal event, a water event, a measurement, a load on machinery, and then the next breath begins. We have followed the cascade. Now another question appears. If these systems work, why do they have these particular sizes? Why are solar arrays so large? Why are modules shaped the way they are? Why use several connected volumes instead of one enormous room? Why use regenerative systems for some resources and resupply for others? Why are radiators outside? Why does the station use a mixture of automatic control and human maintenance? Why not build everything larger, stronger, thicker, and more redundant? Because every improvement has a cost. Mass, power, volume, complexity, crew time, launch capability. The station is not the result of choosing the biggest solution. It is the result of choosing enough. Enough air movement, enough power, enough cooling, enough shielding, enough redundancy, enough space, enough repair capability. The next phase is about that difficult word. Enough. Let's wonder about it. There is no perfect space station. There cannot be. A perfect station would need no maintenance, no resupply, no repairs, no propellant, no replacement parts. It would recycle everything, protect against everything, generate unlimited power, provide unlimited space, and weigh almost nothing. Physics has declined this proposal, so engineers do something more useful. They optimize. Optimization is the art of deciding where perfection is unnecessary and where failure is unacceptable. It is the art of choosing enough strength, enough margin, enough redundancy, enough capacity, enough protection, enough comfort, enough flexibility. A station is therefore not a collection of maximums. It is a collection of negotiated values. Begin with the shape of a pressurized module. Many station modules are cylindrical or approximately cylindrical. This is not because cylinders look especially futuristic, although decades of science fiction have certainly enjoyed the arrangement. Curved pressure vessels are structurally useful. Internal pressure pushes outward. A rounded shape can distribute those loads efficiently. Sharp corners can create stress concentrations and complicate pressure vessel design. A cylinder also fits the geometry of many launch vehicle payload fairings. The module must survive launch before it can become a room. This is one of the hidden constraints behind station architecture. A module may spend years in orbit, but its shape is partly determined by a few violent minutes of ascent. It must fit inside or upon a launch vehicle. It must survive vibration, acceleration, acoustic loads. Then after reaching orbit, it becomes architecture, a laboratory, a bedroom, a storage area, a passage. The launch vehicle shapes the room long before the first astronaut floats through it. This is why modular construction became so useful for the International Space Station. The entire station could not be launched as one complete object. It was too large, so it was divided. Modules and structural elements were launched separately, then assembled in orbit. This created complexity. Every connection needed engineering. Assembly required missions, robotic operations, spacewalks, careful sequencing. But modularity solved another problem. It allowed a structure larger than any single launch could carry. Optimization often works this way, except one kind of complexity. To escape a harder limitation, the station grew piece by piece. A module arrived, then another, a truss segment, solar arrays, laboratories, nodes, airlocks, external equipment. The final architecture emerged from a sequence. This also allowed international partners to contribute major elements. The station became physically modular and institutionally modular. Different organizations built different pieces. Interfaces became essential. A module built in one place had to connect with hardware built elsewhere. Mechanical connections, electrical connections, data connections, atmospheric connections, thermal relationships. The station became an exercise in agreement made physical. A bolt pattern can be diplomacy. A docking standard can be diplomacy. A shared pressure boundary can be diplomacy. Engineering interfaces are promises. This part will fit that part. This signal will be understood. This pressure will be maintained. This vehicle can arrive. Optimization therefore happens not only inside machines, it happens between organizations. Now consider the station's solar arrays. Why so large? Because sunlight contains abundant energy, but photovoltaic conversion is not perfect. The station has substantial electrical demands. The arrays need enough collecting area to generate useful power under orbital conditions, but making arrays larger adds mass, structure, complexity, control challenges, launch packaging challenges. The arrays must be deployed after launch. They must survive the environment. Their orientation relative to the sun matters. So their size reflects a balance, power gained, against everything required to create and manage the collecting surface. The same is true of radiators. A radiator needs area. Thermal radiation depends on temperature, surface properties, and area. More area can allow more heat rejection. But area requires structure, mass, deployment, suitable orientation, protection from damage. The station's exterior therefore becomes a competition for geometry. Solar arrays want sunlight. Radiators want to reject heat effectively. Antennas need communication paths. Visiting vehicles need approach corridors. Robotic systems need working volume. Experiments need exposure. Thruster plumes must be considered. The station is not merely designed in 3 dimensions. It is designed in moving 3 dimensions. The geometry changes as components rotate, vehicles arrive, the station changes attitude, the sun moves relative to the orbital path. Optimization becomes choreography. Now consider the atmosphere. Why not simply use pure oxygen at a lower pressure? Some earlier spacecraft environments used different atmospheric strategies, but atmosphere design involves trade-offs, involving fire risk, human physiology, structural pressure, operational compatibility, and mission architecture. A station intended for long-duration habitation and frequent visiting vehicles benefits from an atmosphere broadly compatible with ordinary human activity and operational requirements. The exact atmospheric management strategy must balance oxygen concentration, total pressure, fire safety, equipment needs, and crew health. Again, there is no single variable to maximize. More oxygen is not automatically better. More pressure is not automatically better. The useful answer lies inside a range. Now return to carbon dioxide. Why not remove every trace? Because zero is not necessary. Human beings can tolerate low concentrations of carbon dioxide. Removal systems require power, hardware, maintenance. The goal is not absolute absence. The goal is acceptable concentration. This is optimization. Do enough work to maintain habitability. Do not spend infinite resources chasing a condition that provides no meaningful additional benefit. The same logic applies to temperature. The station does not need every surface and every corner to have exactly the same temperature. It needs thermal conditions that remain within acceptable limits for people and equipment. The same applies to humidity, pressure, power reserves, orbital altitude. Engineering lives in ranges. The station survives inside them. Now consider redundancy. Why not install 10 copies of every essential machine? Because copies have mass, volume, power connections, maintenance requirements, spare parts, complexity. More redundancy can improve resilience, until the burden of redundancy begins creating other problems. So designers identify critical functions. They consider failure modes. They provide backup capabilities where needed. They may use dissimilar methods so that one common failure does not disable every option. Consumables can provide backup to regenerative systems. Visiting vehicles can contribute capabilities. Crew procedures can compensate temporarily. The goal is not to make failure impossible. The goal is to prevent a single failure from becoming unrecoverable where practical. This is a subtle difference. A robust station expects trouble. It simply refuses to let every trouble become the last trouble. Nothing up here happens by itself, and nothing is duplicated without consequence. Now consider shielding. Why not make the pressure shell extremely thick? Mass. Again. Always mass. A thick wall may improve resistance to some threats, but every additional kilogram must be launched. Layered shielding can sometimes provide better protection against high-speed small particles for a given mass than simply adding one solid slab. The spacing between layers becomes useful. Empty distance becomes part of the shield. This is optimization through geometry. The station uses space itself as a component. Now consider the crew. Why not automate everything? Automation is powerful. Computers can monitor systems continuously. Controllers can react quickly. Robotic systems can perform tasks. But a long-duration station encounters unexpected conditions. Humans can improvise, diagnose, repair, reconfigure, interpret unusual combinations of evidence. A person can open a panel, move a cable, replace a component, notice a smell, hear a sound, see a droplet where no droplet should be. The crew is not merely payload. The crew is part of the station's fault tolerance. But humans require life support. Food, water, space, exercise, sleep, training, protection. Every astronaut increases capability and demand. So crew size is also an optimization problem. More people can perform more work, but more people consume more resources and produce more waste and heat. The station must support the crew it carries. The crew must justify the support it requires. This is not a cold calculation. It is simply the architecture of a closed habitat. Every person becomes part of the mass flow. Oxygen in, carbon dioxide out, water in, wastewater out, food in, waste out, heat out, work produced, knowledge produced, experiments performed. repairs completed. The human being is both load and capability. Now consider sleep. Why attach a sleeping bag to a wall? Because a bed is unnecessary in microgravity. There is no need for a mattress to support body weight. A person can sleep in almost any orientation, but complete freedom to drift may be inconvenient. The sleeper could move into equipment, block airflow, bump into surfaces. So the sleeping bag provides a stable personal location. It creates a small sense of place. And ventilation remains important. The crew quarters need airflow. The sleeping astronaut continues producing carbon dioxide. So our question returns. Why does a space station need fans to keep a sleeping astronaut alive? Because optimizing a habitat does not mean recreating Earth perfectly. It means recreating the functions that matter. A space station does not need gravity to pull a sleeping body onto a mattress, so it does not spend resources creating a conventional bed. But it does need airflow to move exhaled carbon dioxide, so it spends power on ventilation. This is optimization at its purest. Do not copy the appearance of Earth. Copy the necessary function. A bed is optional. Gas exchange is not. A floor is optional. Orientation cues are useful. A shower is optional. Hygiene is not. Fresh river water is unavailable. Clean water is essential. Outdoor air is unavailable. Atmospheric renewal is essential. The station is full of things that look different because engineers preserved the function and discarded the terrestrial habit. Consider the toilet. On Earth, gravity moves waste away from the body. In microgravity, airflow can help perform that function. The station replaces gravity with controlled suction. Again, do not recreate the appearance, recreate the function. The result may look unfamiliar. But physics does not care whether a bathroom feels traditional. It cares whether waste goes where it should. The same principle shapes exercise equipment. Do not carry heavy iron weights merely because gyms on Earth use them. Create resistance another way. Preserve loading. Discard unnecessary dependence on weight. The same principle shapes cooling. Do not install an outdoor fan and expect vacuum to carry heat away. Move heat to radiators. Preserve heat rejection. Discard the assumption of surrounding air. The station is optimized by separating needs from habits. This may be the most useful way to understand its strange appearance. Every unfamiliar machine is asking, what did Earth used to do for us? And what is the lightest reliable way to replace that service here? Gravity used to move waste, use airflow. Convection used to move warm air, use fans. Rivers and infrastructure used to provide water, recover it. The atmosphere used to absorb heat, use radiators. The ground used to resist our muscles, use exercise machines. A vast biosphere used to process waste, build smaller chemical and mechanical loops. The planet used to provide shielding, add material and manage exposure. Earth used to be the system. Now the station must become one. Nothing up here happens by itself. Optimization is the process of deciding how much Earth to rebuild, not visually, functionally. And the answer is always incomplete. A station does not recreate the entire planet. It creates a narrow corridor of conditions in which humans can continue living and working. A small atmospheric bubble, a controlled temperature range, a water loop, a power system, a pressure shell, a place to exercise, a place to sleep, a path for waste, a connection to Earth. That is enough. Not forever, not independently, but long enough, reliably enough, repairably enough. This word, enough, may be the true shape of every successful spacecraft. The solar arrays are large enough, the radiators are large enough, the modules are strong enough, the shielding is protective enough for the mission and design assumptions. The life support systems recover enough, the backups provide enough time, the station carries enough supplies, the crew has enough room to work, the orbit is high enough to remain useful, but low enough to retain the advantages of low Earth orbit. Every dimension sits inside a compromise, and compromises have costs. A regenerative system saves resupply mass, but adds machinery. Large solar arrays provide power, but adds structure and control challenges. Redundancy improves resilience, but adds mass and complexity. Modularity enables assembly, but creates interfaces and seals. Human crews provide adaptability, but require extensive life support. A low Earth orbit station is easier to reach than a deep space habitat, but still experiences atmospheric drag. The elegant solution is never free. And now, we are ready to examine the price, not money alone, mass, complexity, maintenance, risk, crew time, dependence. The costs hidden behind every successful loop. Let's go find them. Every solution aboard a space station arrives carrying luggage. Sometimes the luggage is mass, sometimes power, sometimes heat, sometimes noise, sometimes maintenance, sometimes complexity, and sometimes the solution to one problem quietly becomes the source of another. This is not poor engineering, it is the unavoidable shape of engineering. A station cannot choose a benefit without asking what the benefit costs. The solar array provides electricity, but it has mass. It requires structure, it must be deployed. Its orientation matters. It ages in the space environment. The battery carries energy through darkness, but it has mass. It produces heat. It has a finite operating life. The fan moves air, but it consumes electricity. It creates noise. Its moving parts can wear. The water recovery system reduces the amount of replacement water that must be launched, but the recovery system itself requires machinery, power, filters, sensors, maintenance, spare parts, crew attention. The carbon dioxide removal system protects the atmosphere, but it too requires energy, hardware, control, regeneration, repair. Nothing up here happens by itself, and nothing useful happens for free. Begin with the most basic trade. Open systems against closed systems. An open system can be simple. Carry a supply, use it, discard the waste. For a short mission, this can be an excellent solution. There may be no reason to build an elaborate recycling machine if the mission ends before the savings justify the machinery. A short journey can carry water, carry oxygen, carry food, then return. But as mission duration increases, the arithmetic changes, consumables accumulate. The mass of replacement supplies grows. At some point, carrying a machine that recovers a resource may become more useful than carrying all the resource that would otherwise be needed. But the machine introduces its own costs. This means there is no universal answer to the question, should we recycle this? The answer depends on duration, crew size, distance, available power, reliability, maintenance, launch capability, the difficulty of resupply, the value of the recovered material, and the consequences of failure. A machine that saves mass over 5 years may be pointless for 5 days. A machine that is acceptable near Earth may be too dependent on replacement parts for a journey to Mars. Optimization depends on context, and context changes with distance. The International Space Station can receive cargo. That fact shapes almost everything. Food arrives, experiments arrive, replacement equipment arrives, spare parts arrive. Some gases and water can be resupplied. The station can therefore use a mixture of recycling and delivery. It does not have to close every loop. This is important. The International Space Station is not a completely self-sufficient world. It is part of a larger transportation system. The station works partly because rockets keep arriving. Its apparent isolation is incomplete. A person can look through a window and see nothing nearby. Yet the station remains connected to factories, launch sites, control centers, warehouses, tracking networks, scientists, engineers, ships, aircraft, computers, and thousands of people on Earth. The station is not one machine, it is the orbital end of a planetary supply chain. This creates a trade-off. Resupply allows the station to avoid carrying machinery for every possible form of recycling or manufacturing, but resupply creates dependence. A launch can be delayed, a vehicle can encounter a problem, a replacement part may not be immediately available, so the station carries reserves, spare parts, redundant capabilities, operational margins. Again, more resilience means more mass. The trade never disappears. It simply changes form. Now consider redundancy. Suppose one machine performs a critical function. If that machine fails, the function is lost, so perhaps a second machine is added. Now the system can survive one failure, but the second machine adds mass, volume, power connections, control interfaces, maintenance requirements, potential failure modes of its own. Perhaps the two machines share a common power source. Then one failure in the power source can affect both. Perhaps they share cooling. Then a thermal problem can affect both. Perhaps they are identical. Then the same design flaw could exist in both. So true resilience is not simply counting machines. It requires understanding how failures propagate. Two machines are not fully independent. If one cable can disable both, three sensors are not useful if they all depend on the same failed computer. A backup is only a backup if the path to it remains available. This is why spacecraft systems can become complicated. Engineers do not merely ask, what can fail? They ask, what else fails when it does? A pump stops. Does cooling stop? If cooling stops, which equipment overheats? If that equipment shuts down, which other systems lose capability? How long before temperature limits are reached? Can another loop carry the load? Can the crew reconfigure valves? Can non-essential equipment be turned off? How much time exists? The trade-off becomes a tree of consequences. The station survives partly because those trees are studied before the first branch breaks, but not every branch can be predicted. Real operation always teaches something new. This is where human crews become valuable. Automation can respond to known conditions. People can sometimes respond to combinations nobody expected. But humans introduce their own trade-offs. A person can repair a machine. A person also needs oxygen, water, food, temperature control, waste management, exercise, sleep, medical support, protection, space. Every crew member increases the station's capability and its metabolic load. More people can perform more science, more maintenance, more observations, more repairs. But more people also produce more carbon dioxide, more humidity, more heat, more waste. The life support system must scale, the food supply must scale, the return capability must scale. A station cannot simply add another person as though adding another chair to a room. The person becomes part of every resource equation. This is why crew capacity is not merely a question of physical space. A module may contain enough volume for another person. That does not mean the station can support another person indefinitely. The atmosphere must support them. The water system, the food supply, the emergency return plan, the exercise equipment, the sleeping arrangements, the toilet, perhaps especially the toilet. Spaceflight has a way of returning grand ambitions to plumbing. Now consider recycling. The phrase sounds automatically good. Recover more, waste less, launch less. But every percentage of additional recovery can become harder than the percentage before it. The easiest water may be recovered first. The remaining water may be bound inside more difficult waste streams. Recovering it may require more energy, more machinery, more maintenance. At some point, the cost of recovering the final fraction may exceed the benefit for a particular mission. So engineers ask a difficult question. How closed should the loop be? Not, can we theoretically recover more, but should we? A perfectly closed system would be extraordinary. It would also be extraordinarily difficult. Real systems leak material. Filters are replaced, waste leaves, food arrives, gases may be vented, chemical processes produce outputs that are not fully recovered. The goal is not perfection for its own sake. The goal is mission sustainability. This is why the station can recover much of its water while still receiving supplies from Earth. The loop is useful even when it is incomplete. A circle with a small gap can still save enormous amounts of resupply mass compared with a straight line. Now return to our breath. Why does a space station need fans to keep a sleeping astronaut alive? Because forced ventilation solves the problem of stagnant air. But the fan creates a trade-off. Noise. A fan that moves enough air may be heard. Many machines aboard a station operate continuously. Fans, pumps, computers, ventilation equipment, life support machinery. The station is not silent. This surprises some people. Space outside may be vacuum, but the cabin is full of air. Sound travels through that air. Vibration travels through structure. The station can hum, whir, click, buzz. The machinery keeping the crew alive can also make sleep more difficult, so acoustic control matters. Equipment may be designed to reduce noise. Sound levels can be measured. Crew hearing must be protected. A machine that performs perfectly but makes the habitat intolerably loud is not a perfect machine. Human comfort is not separate from engineering. It is one of the requirements. This creates another trade. Move enough air, but not so violently that the cabin becomes unnecessarily noisy. Cool the equipment, but manage the sound of the fans. Provide alarms, but avoid an environment where constant, unnecessary alerts destroy attention. Provide lighting, but support sleep. Provide workspaces, but preserve some privacy. The station is a machine and a home. Those identities sometimes disagree. A machine wants efficient access to equipment. A home wants calm. A machine wants ventilation. A sleeper wants quiet. A laboratory wants experiments. A crew member wants room. A cargo vehicle brings supplies. Then the supplies need storage. The station must negotiate between function and livability. This is why habitability matters. Humans are not components that can be bolted into an empty corner. People need routines, personal space, sleep, food, communication with family, moments away from work. A long-duration habitat must support psychology as well as physiology. The station may be an extraordinary laboratory, but for the crew, it is also where the day ends. There is no commute home. The workplace remains outside the sleeping compartment. The machinery continues. Earth remains visible through a window, but unreachable without a spacecraft. This creates a strange trade-off between connection and isolation. The crew can communicate with the ground, messages, voice, video, operational communication, personal communication. Yet physical separation remains. A conversation can cross the distance quickly. A person cannot. Low Earth orbit is close by astronomical standards, but it is still beyond ordinary rescue. The crew lives in a place where help is both near and far. This shapes station design. Emergency procedures matter. Visiting crew vehicles can provide a means of return. The station must maintain the ability to respond to serious conditions: fire, loss of pressure, atmospheric contamination, medical problems. The exact response depends on the event, but the trade-off is always present. The station is valuable because people remain there. People remain there only because there are acceptable ways to leave when necessary. A habitat must also be an evacuation problem. Now consider the pressure shell. Make it stronger. That sounds good, but stronger may mean heavier. Make it lighter. That sounds good, but margins may decrease. Add more shielding. Protection improves. Mass increases. Add more windows. The crew gains views. Scientists gain observation opportunities. But windows are complicated structures in a pressure vessel. They must withstand pressure, thermal conditions, the external environment. They require protection. A wall is simpler. A window is valuable. The station chooses both. The famous view of Earth is therefore not free. It exists because engineers accepted the complexity required to create a transparent boundary between a pressurized habitat and space. A person can float beside that boundary and look down: blue ocean, white cloud, brown land, the thin atmospheric glow, a planet filling the view. But the window is still part of a spacecraft. It has layers, protection, operational rules. The poetry rests inside engineering. Now consider modularity. Building the station from separate pieces made the project possible, but every connection between modules creates an interface. An interface can fail, a seal can leak, A connector can have a problem. A hatch occupies space. A passage may be narrower than the modules it connects. Cables and data must cross boundaries. Air must circulate between volumes. The benefit of modularity is expansion and assembly. The cost is interfaces. This principle appears everywhere in engineering. A single integrated object may have fewer connections. A modular object may be easier to build, replace, expand, or distribute among partners. The International Space Station chose modular growth because no single launch could deliver the completed structure. The cost was an enormous assembly campaign. Flights, robotics, spacewalks, integration, years. The station became possible by accepting complexity over time. Now consider repairability. A machine can be made compact by sealing everything inside a tightly integrated enclosure. But if a component fails, can the crew reach it? A more accessible design may occupy more space, require connectors, panels, fasteners, clearances, labels. The trade is compactness against maintenance. On Earth, a broken appliance can be removed and replaced. In orbit, replacement may not be immediately available. So access matters. Tools matter. Documentation matters. The ability to isolate a system matters. The ability to work around a failed component matters. A space station must not only function, it must be understandable while malfunctioning. That is a very different design requirement. A machine can be beautifully efficient when healthy, and terrible to repair. Long-duration spacecraft cannot afford to admire that kind of beauty for long. The elegant machine is often the one a tired person can fix. This introduces another human trade-off: crew time. Every hour spent maintaining the station is an hour not spent performing research or other mission tasks. But without maintenance, there may eventually be no station in which to perform research, so maintenance competes with the mission, while also enabling the mission. The station consumes some of its own purpose simply to continue existing. This is true of every long-lived infrastructure system. Cities maintain roads, ships maintain engines, hospitals maintain equipment, bodies maintain cells. A space station is no different. Survival has overhead. The more complex the habitat becomes, the more attention it may require. Automation can reduce some workload, but automation itself requires software, sensors, computers, testing, updates, fault management. A highly automated system may reduce routine human intervention, while becoming more difficult to understand when something unusual happens. Again, a trade. There is no final escape. Now consider the external environment. The station needs radiators to reject heat. Large external surfaces are useful, but external surfaces are exposed. Micrometeoroids, orbital debris, atomic oxygen, ultraviolet radiation, thermal cycling. Every square meter added to the exterior becomes another square meter interacting with space. Solar arrays need area. Radiators need area. Area creates capability. And exposure. The station must accept the environment in order to use it. Sunlight provides energy. Sunlight also heats surfaces and contributes to material degradation. Low Earth orbit keeps the station relatively close to Earth. Low Earth orbit also contains residual atmospheric drag. Earth's magnetic environment provides significant protection compared with deep space, but radiation exposure remains greater than on the ground. Every location is a package of advantages and costs. There is no orbit called perfect. The International Space Station occupies an orbital regime that makes crew and cargo access practical compared with more distant destinations. It allows frequent communication, it supports Earth observation, it provides microgravity, but the station still needs reboosts, still encounters debris, still experiences radiation, still requires launch vehicles to reach it. The orbit solves some problems by accepting others. Now consider propulsion. Thrusters can change orbit, assist with attitude control, help manage momentum. But propulsion consumes propellant. Propellant is finite. It must be launched, so the station does not want to use thrusters unnecessarily. Control moment gyroscopes can provide routine attitude control without consuming propellant in the same way, but gyroscopes have limits. they can become saturated with accumulated momentum. Then thrusters may be needed to unload them. The optimized system combines methods. Use the resource-conserving method when possible. Use propellant when necessary. This is more complex than choosing only one method, but it reduces the cost of continuous operation. The same philosophy appears in life support. Recycle when useful. Resupply when practical. Store backups. Use multiple methods. Do not demand that one system solve every condition. Resilience often comes from diversity, but diversity creates training demands. The crew must understand more equipment. Ground teams must support more systems. Spare parts become more varied. Software becomes more complex. Again, the luggage arrives. Every benefit brings a bag. Now consider scientific research. The station exists partly as a laboratory. Experiments need power, data, crew time, cooling, storage, sometimes special facilities. But the station's primary systems must remain safe. An experiment cannot simply consume unlimited resources. Scientific ambition must fit within operational constraints. Power is scheduled, crew time is scheduled, cargo is scheduled. Experiments may wait. The laboratory itself is a trade between exploration and survival, and sometimes the station becomes the experiment. A new life support technology can be tested. A new material can be exposed outside. A new exercise method can be studied. A new robotic technique can be demonstrated. The station provides something rare, time in space. Long duration operation reveals what short tests cannot. A component may work perfectly for a week, then behave differently after a year. A human body may adapt differently over months than over days. Microorganisms may behave in unexpected ways. Materials age, systems foul, filters load. The station allows engineering to encounter time, but long-duration testing costs time too. Years of operation require maintenance, funding, launches, people. The station becomes expensive partly because duration itself is expensive. To keep something alive in orbit, you must keep supporting it. This brings us to perhaps the largest trade-off of all. A space station gives humans a place to live beyond Earth, but to create that small place, an enormous system on Earth must exist. Factories build hardware, launch vehicles carry it, control centers support it, tracking systems follow it. Scientists design experiments, engineers investigate failures, medical teams study crews, ships and aircraft may support returning spacecraft. International agreements coordinate participation. The station is small in orbit and enormous on the ground. Its true footprint cannot be seen in a photograph. The familiar image shows solar arrays against black space. It does not show the thousands of people connected to them. This is why the station can never be fully understood as an isolated object. Its independence is partial. Its self-sufficiency is partial. Its loops are partial. And that is enough. Enough to keep people living continuously in orbit. Enough to learn. Enough to test. Enough to discover which systems are worth carrying farther from Earth. Because every trade-off changes with distance. Near Earth, a spare part can arrive on a later mission. Farther away, perhaps not. Near Earth, crews can return relatively quickly compared with deep space missions. Farther away, the habitat must become more autonomous. Communication delays grow, resupply becomes harder, repairability becomes more important, recycling becomes more valuable, manufacturing parts locally becomes more attractive. The International Space Station, therefore, does not represent the final answer to living in space. It represents a vast collection of questions made operational. How much can we recycle? How often do systems fail? What does long-duration microgravity do to the body? How much maintenance does a regenerative system require? How should crews exercise? How do materials age? How do people work in a confined orbital habitat? How do international teams operate one machine? How do you repair something that cannot be brought back to a workshop? How do you sleep beside the machinery keeping you alive? And our small question remains inside all of them. Why does a space station need fans to keep a sleeping astronaut alive? Because removing gravity from ordinary life reveals how much Earth normally does for us. On Earth, the room helps move air through natural convection. The planet provides an atmosphere. Infrastructure provides water. Gravity moves waste. The environment absorbs heat. The ground loads bones and muscles. A vast biosphere cycles materials. In orbit, every missing service becomes a design decision, and every design decision has a cost. The fan costs power. The power system costs mass. The mass costs launch capability. The fan creates heat. The heat requires cooling. The fan creates noise. The noise must be managed. The fan can fail. The failure requires redundancy or repair. One small machine. One long chain of trade-offs. Nothing up here happens by itself, and nothing up here exists alone. This is the price of the elegant solution. Loops create sustainability, but loops require machinery. Redundancy creates resilience, but redundancy requires resources. Human crews create adaptability, but humans require a habitat. Large structures create capability, but large structures require assembly. A station survives because these costs were not eliminated. They were accepted, measured, balanced, and revised. The design did not emerge complete, it evolved. Before the large station, there were smaller stations. Earlier crews learned how to remain in orbit, how to dock, how to work, how to exercise, how to repair, how to assemble, how to live. Failures taught lessons. Successes taught different lessons. Each generation inherited questions from the one before it. The space station we know today was not imagined from nothing. It grew from decades of experiments in habitation, small modules, short stays, longer stays, docking missions, orbital workshops, modular stations, international cooperation. The trade-offs were tested in real metal, with real people inside. And that is where we go next, not into a machine, but backward through time, to see how humans slowly learned to build a place where someone could close their eyes, float inside a sleeping bag, and trust the fans to keep turning. Let's go find it. Before a space station could become a place where people lived for months, it first had to become a place where people could arrive at all. That sounds obvious. But the ability to place a human in orbit is not the same as the ability to maintain a human presence there. A capsule can carry people through space. A station asks for something more difficult: duration, the difference between visiting space and inhabiting it. The earliest human space flights were brief. They answered foundational questions. Could a person survive launch? Could a person function in weightlessness? Could a spacecraft maintain a habitable environment? Could a human return safely? These were not small questions. Before they were answered, everything that came later was uncertain. A long-duration station would have been meaningless if the human body could not tolerate even short periods in orbit. So the first step toward the space station was not a station. It was proof. A person could go. A person could remain for a while. A person could work. A person could come back. Then the duration grew. Hours became days. Days became weeks. Spacecraft began meeting one another. Rendezvous became possible. Docking became possible. These capabilities were essential. A station that cannot receive vehicles is limited by whatever it carried at the beginning. A station that can receive vehicles can become part of a transportation network. Crew can rotate. Cargo can arrive, equipment can be replaced. The habitat gains a future. Rendezvous and docking therefore changed the meaning of orbit. Two spacecraft no longer had to remain separate worlds. They could meet, connect, exchange people and material. This was one of the great conceptual steps toward permanent habitation. A station is not merely a destination, it is a destination with a door. The door must be reached precisely. Orbital mechanics makes this more complicated than approaching a building on Earth. A spacecraft cannot simply stop beside the station. Both vehicles are moving around Earth. Their orbits must be shaped so that they arrive at nearly the same place at nearly the same time with carefully controlled relative motion. A small change in velocity can alter orbital period and geometry. Approach is therefore built from prediction, maneuver, observation, correction, patience. The final distance may close slowly, but the path began far earlier. Once docking became reliable, stations could become more ambitious. In the early 1970s, the Soviet Union launched Salyut 1, the first space station. For the first time, a crewed orbital facility existed as a destination separate from the spacecraft that carried people to it. The idea of a station had become physical. The station was small compared with later complexes, but scale is not the important point. A new category of human environment had appeared, a place in orbit designed for habitation and work. The early era was not smooth. Spaceflight rarely learns without cost. Missions revealed the difficulty of docking, long-duration operations, life support, crew health, return. Each experience added knowledge. The station was becoming not merely a spacecraft type, but a discipline. The United States followed with Skylab. Launched in the year 1973, Skylab was built from hardware associated with the Saturn program. Its large internal volume gave crews a different kind of orbital environment. Astronauts lived and worked there during missions lasting weeks. They conducted scientific observations, studied the Sun, observed Earth, performed experiments, and learned more about the human body's response to extended weightlessness. Skylab also demonstrated something that would become central to future stations: repair. The station experienced serious problems during launch. A micrometeoroid shield was lost. A solar array was damaged. Another solar array failed to deploy properly. The station faced thermal and power difficulties. The first crew arrived not merely as occupants, but as repairers. They deployed a replacement sunshade, worked to free a stuck solar array, restored capability. The lesson was profound. A station did not need to be perfect when it arrived. If people could reach it, understand it, and work on it, the station could recover. Human adaptability became part of spacecraft design. The crew was not merely consuming life support. The crew was providing resilience. This is one of the reasons long-duration human spaceflight remains so interesting. A robot can be extraordinarily capable, but a person can encounter a problem never fully anticipated. Look at it, discuss it, use tools, and improvise. That flexibility has mass and metabolic costs, but it also has enormous value. Skylab made that value visible. The station survived because people could intervene. Later, the Soviet and then Russian station programs pushed long-duration habitation further. The Salyut stations accumulated experience. Then Mir expanded the idea of modular construction. Launched beginning in the year 1986, Mir grew as additional modules were attached over time. The station became a complex assembled in orbit. This was a major step toward the architecture that would later define the International Space Station. A station no longer had to be launched as one complete object. It could grow. A core could be placed in orbit. New modules could arrive later. Capabilities could be added. Laboratories, living areas, docking interfaces. The station became evolutionary, not merely in the historical sense, in the physical sense. Its body changed. Modularity solved the launch size problem by accepting an assembly problem. The station could become larger than one rocket's payload, but only if many launches succeeded, only if rendezvous worked, docking worked, interfaces worked, crews and robotic systems could integrate the new elements. The architecture depended on repetition: launch, approach, connect, activate, use, then do it again. Mir also became a long-duration laboratory for human endurance and station maintenance. Crews lived aboard for extended periods. Systems aged. Repairs became part of daily life. The station experienced serious incidents. A fire occurred aboard Mir in the year 1997. Later that year, a Progress cargo spacecraft collided with the station during a docking test, damaging a module and causing depressurization. The crew had to respond. A hatch was closed to isolate the damaged module. Cables passing through the hatchway complicated the effort. The event revealed the reality of modular survival. A station can become several compartments. A damaged volume can be isolated. But real spacecraft are messy. Cables cross boundaries. Equipment connects spaces. Emergency procedures meet physical details. The station teaches through specifics, not through diagrams alone. Mir demonstrated both the promise and the difficulty of long-duration orbital habitation. A station could remain occupied for years. It could be repaired, expanded, resupplied, visited by international crews, but long operation exposed wear, failures, human workload, the demands of maintenance. The lessons were not evidence that stations did not work. They were evidence of what working actually required. Nothing up here happens by itself. By the time the International Space Station began assembly, decades of experience had accumulated. Short flights had become long flights. Rendezvous had become routine enough to support repeated visits. Docking had matured. Spacewalks had become a major construction capability. Robotic arms could manipulate large objects. Life support had evolved. Solar power systems had grown. Computers had changed. International partnerships had formed. The new station would combine these histories. Its first element, Zarya, launched in November of 1998. Soon afterward, the Unity connecting module arrived aboard the Space Shuttle Endeavour. The two elements were joined in orbit. This was the beginning of an assembly process that would continue for years. The station did not appear all at once, it accumulated. A module arrived, then another, a truss, a laboratory, solar arrays, nodes, airlocks, robotic systems, international elements. Each addition changed the station. More volume, more power, more capability, more mass, more complexity. The assembly sequence had to be carefully planned because later steps depended on earlier ones. A component might need power before another component could arrive. A connection point had to exist before a module could be attached. Robotic systems had to be available. Crew access had to be possible. The station was not assembled like furniture from a single box. It was assembled while operating. Imagine constructing a building. While the building is already occupied, while the construction site circles Earth, while every major new room arrives on a rocket. This is the peculiar achievement of orbital assembly. The worksite cannot pause its orbit. The existing station must remain safe. The crew must continue living, power must continue, thermal control must continue, communications must continue. Then a new piece arrives. The station changes. This required spacewalks. Astronauts worked outside the pressurized environment wearing spacesuits that functioned as tiny independent spacecraft. A spacesuit provides pressure, oxygen, carbon dioxide removal, temperature control, communications, protection. The astronaut leaves one life support system and enters another. A station outside a station. The crew member moves through vacuum carrying a personal atmosphere, then works on a structure larger than a house. The contrast is extraordinary. A human hand in a pressurized glove, connecting hardware that will support an international laboratory. Spacewalks helped route cables, install equipment, connect structural elements, repair systems, upgrade hardware. The station was assembled through thousands of actions: turn a fastener, connect a cable, move a component, check a seal, install a handrail, one small action, then another. The finished silhouette emerged from details. Nothing up here happens by itself. And nothing large is built without small work. As the station grew, its internal systems grew too. More crew required more life support. More laboratories required more power. More power created more heat. More heat required thermal control. More modules required airflow between volumes. More equipment required maintenance. Growth created capability and load. The station had to evolve as a system. This is why adding a module is not merely adding a room. The room must join the metabolism of the station. Power, data, atmosphere, cooling, structure, operations. A module becomes alive in the mechanical sense only when it joins the loops. This brings us back to the fan. Why does a space station need fans to keep a sleeping astronaut alive? Because as stations evolved from short-duration vehicles into large connected habitats, the atmosphere became larger and more complicated. Air had to move through connected volumes, crew quarters, laboratories, nodes, passageways, equipment areas. The station could no longer depend on one small cabin behaving uniformly. Ventilation became part of the architecture. A sleeping person in one compartment still needed to remain connected to the larger atmospheric management system. The fan became a bridge between local life and station-wide machinery, and the evolution continues. Life support systems are upgraded, new experiments test more efficient recycling, new vehicles visit, new docking systems are used, new commercial spacecraft carry crews and cargo. Old hardware is maintained beyond the era in which it was first imagined. The station has become a layered machine. Different generations of technology coexist. A component designed decades ago may operate beside newer hardware. Software changes, computers are replaced. Experiments arrive with modern electronics. The station becomes a timeline you can float through. This is another consequence of longevity. A long-lived machine accumulates history. A newly launched spacecraft can be technologically uniform. A station operating for decades becomes archaeological. Panels hide older infrastructure. New cables follow paths through existing structure. Upgrades adapt to what is already there. The station is not rebuilt from scratch every year. It grows around itself. This creates another form of evolution. Operational evolution. Crews learn better procedures. Ground teams refine methods. Maintenance histories reveal patterns. Training changes. New tools are developed. A problem that was once unfamiliar becomes routine. The machine may remain physically similar, but the knowledge around it grows. This may be one of the least visible benefits of a long-duration station. Institutional memory. How do you operate a habitat continuously? How do you hand responsibility from one crew to another? How do you maintain systems built by different organizations? How do you coordinate control centers across nations? How do you respond when a failure does not match the textbook? These questions cannot be answered by hardware alone. They require years, people, experience, mistakes, revision. The station teaches organizations how to live in space too. Not only astronauts. Entire institutions learn. And this learning has already begun moving outward. Future stations can inherit what worked, discard what did not, improve recycling, reduce maintenance, increase automation, use newer materials, adopt different assembly methods, support commercial activity, operate in different orbits. The International Space Station is therefore both a destination and an ancestor. Its descendants do not need to look exactly like it. Evolution rarely copies the entire parent. It preserves useful functions, changes the rest. Future stations may be smaller, more automated, commercially operated, designed for different crew sizes, built for different scientific or industrial goals. Stations near the moon may face different radiation conditions, different communication delays, different resupply challenges, different orbital dynamics. A system optimized for low Earth orbit may not be optimized elsewhere. The fan may remain, the pump may remain. The need for air, water, power, cooling, pressure, maintenance. Those functions persist, but the machinery can change. This is how engineering evolves, not by abandoning old problems, by finding new ways to answer them. The first stations proved that people could inhabit orbit. Later stations extended duration. Modular stations proved that orbital complexes could grow. The International Space Station expanded assembly, international operation, research and long-duration habitation on an unprecedented scale. The next stations will inherit the questions. How much can be automated? How much can be recycled? How much maintenance can be reduced? Can parts be manufactured in orbit? Can stations be assembled more efficiently? Can habitats operate farther from Earth with less immediate support? Can commercial stations make continuous human presence in low Earth orbit more diverse? Each generation will carry different trade-offs, but the oldest question remains: can a human close their eyes and trust the habitat? That is the test. Not the launch, not the photograph, not the first docking, the ordinary night, the moment when nothing spectacular is happening. A person sleeps, the station continues, Fans turn, pumps circulate, computers monitor. The orbit carries everything onward. A technology becomes a habitat when survival can become routine. The evolution of the space station is therefore the evolution of ordinary life in an extraordinary place. At first, simply reaching orbit was extraordinary. Then staying became extraordinary. Then docking. Then weeks. Then months. Then years of continuous presence. The extraordinary slowly became scheduled, maintained, logged, repaired. The frontier acquired maintenance procedures. And perhaps that is progress. Not making space less remarkable, but making human life there more dependable. The station evolved until a sunrise every few orbits could become background, until floating could become normal, until recycled water could become a drink, until an orbital laboratory could have a bedtime. And now, after all this effort to keep humans alive, something unexpected happened. The systems built for survival began producing benefits beyond survival. The station became more than a shelter, more than a laboratory, more than a test bed. The very constraints that made life difficult began revealing new ways to think about water, medicine, materials, robotics, Earth, and closed systems. The problem created the tool created knowledge. The knowledge began traveling home. Let's go find it. A space station is built to keep people alive in a place where they would otherwise die. That is the obvious benefit. Air remains inside, carbon dioxide is removed, water is recovered, electricity is generated, heat is rejected, the orbit is maintained, the crew survives. But once a machine can keep people alive, something interesting happens. The survival system becomes a laboratory. A pump is no longer only a pump. It is a long-duration experiment in reliability. A water processor is no longer only a source of drinking water. It becomes a test of how tightly a human habitat can close its material loops. A crew member is no longer only a resident. The body becomes a source of information about bones, muscles, vision, balance, immunity, sleep, microorganisms, and adaptation. The station begins answering questions that were not the original reason for building every piece of hardware. This is the unexpected benefit of constraint. When a problem becomes difficult enough, the solution may become useful somewhere else. Nothing up here happens by itself, and knowledge does not always stay where it was discovered. Let us begin with water. On Earth, water treatment usually exists inside enormous systems: reservoirs, rivers, pipes, treatment facilities, distribution networks. A city can move vast amounts of water through infrastructure spread across kilometers. A space station cannot. Its water system must fit inside the habitat. Mass matters, volume matters, power matters, reliability matters. The water must be treated repeatedly. Equipment must operate in microgravity. Maintenance must be possible with limited tools and supplies. These constraints push engineers toward compact and efficient methods. The immediate purpose is obvious: reduce the amount of replacement water that must be launched. But the deeper benefit is experience. How do you recover water from difficult waste streams? How do you monitor water quality in a closed environment? How do you design treatment systems that must operate for long periods? How do you reduce consumables? How do you repair a processor when the nearest factory is on another planet? The station turns water into a systems question, and that systems thinking can matter beyond orbit. Remote communities, disaster response, regions where clean water is difficult to obtain, industrial processes, future habitats on the moon, future journeys to Mars. The exact hardware may change, the operating conditions may differ, but the principle travels. Water is not valuable only because you possess it. Water becomes more valuable when you can recover it. This is one of the quiet lessons of closed environments. A river can hide inefficiency. A spacecraft cannot. The station makes waste visible. Every lost liter has a history. It had to be launched, stored, managed, used. If it cannot be recovered, something must eventually replace it. This creates a kind of engineering honesty. The system cannot pretend that waste has disappeared. and this honesty extends to air. Carbon dioxide removal aboard a spacecraft is not identical to the enormous challenge of managing carbon dioxide in Earth's atmosphere. The scales are profoundly different, the goals are different, the technologies are different. But the station offers a clear demonstration of a more general principle. An atmosphere can be monitored, processed, adjusted, and maintained only through continuous work. The cabin feels passive. It is not. The apparent stillness is the result of machinery. The lesson is not that Earth can be treated as a giant space station. Earth is vastly more complex. Its atmosphere interacts with oceans, land, life, weather, geology. But the station gives us a smaller model of dependence. People change their environment simply by living inside it. A closed environment remembers every breath. That is difficult to forget once you have understood it. Now consider medicine. A crew member in orbit is physically separated from ordinary hospitals. Medical support must therefore combine onboard capability with expertise on the ground. Communication allows specialists to support crews remotely. Procedures can be guided. Medical data can be transmitted. Crew members can be trained to perform tasks that might ordinarily involve specialists nearby. This creates experience in remote care. Again, the exact conditions are unusual, but the underlying problem is familiar. What happens when the expert is far away from the patient? How can information travel instead? How can equipment become easier to use? How can a person with limited specialist training perform a useful examination under remote guidance? The station is an extreme version of distance. Extreme versions of problems can reveal tools for less extreme ones. The same is true of ultrasound. A compact imaging device aboard a station can become more useful when crew members can be guided in how to position and operate it. The expertise does not have to occupy the same physical room as the instrument. Knowledge can travel. The hands can be local. The guidance can be remote. This division becomes increasingly important as humans travel farther from Earth. Communication delays will eventually make immediate guidance impossible. A crew near Mars cannot depend on a real-time conversation with a doctor on Earth, so the next step is greater autonomy, more training, better software, better diagnostic tools. The station becomes a bridge. First, remote support. Later, independent capability. Now consider the human body itself. Before long, duration spaceflight. Many effects of extended microgravity could only be predicted. The station allowed them to be measured over months. The body adapts. Bones change, muscles change, fluid distribution changes, balance systems adapt. The cardiovascular system adapts. Researchers can study these changes before flight, during flight, after return. This knowledge is essential for future exploration, but it can also deepen understanding of the body more generally. A person in microgravity experiences unusual patterns of mechanical unloading. Exercise countermeasures attempt to reduce some of the consequences. Researchers study how tissues respond. The station becomes a place where one environmental variable, gravity's usual mechanical effect on the body, is dramatically altered. This does not make every result directly transferable to people on Earth, but it creates a distinctive research condition. The human body reveals different parts of itself when one familiar force is changed. The same principle applies to physical science. On Earth, gravity can dominate fluid behavior. Hot fluid rises, dense material settles, particles sediment, bubbles rise through liquids, flames are shaped by buoyancy-driven flow. Remove the familiar influence of gravity, and subtler effects become easier to observe. This is one of the great scientific advantages of microgravity. It does not remove physics, it rearranges which parts are loudest. Imagine trying to hear a quiet instrument while a drum is playing beside it. Turn down the drum, and something that was always present becomes audible. Microgravity can do this for certain physical processes. Surface tension becomes more influential relative to buoyancy. Diffusion can become easier to isolate. Sedimentation is reduced. Convection changes. Flames behave differently. Materials can be studied under conditions difficult to sustain on Earth. The station is therefore not valuable because gravity is entirely absent. It is valuable because continuous free fall creates a long-duration environment in which gravitational effects are greatly reduced for many experiments. This allows scientists to ask different questions. Consider fire. On Earth, a familiar candle flame has a shape influenced by buoyancy. Hot combustion gases rise. Fresh air is drawn in. The flame stretches upward. In microgravity, that familiar flow changes. Flames can become more spherical under some conditions. Combustion can proceed differently. Researchers can study flame behavior without ordinary buoyancy dominating the process. Why does this matter? Because combustion is complicated. Fuel, oxygen, temperature, flow, chemistry, heat transfer. Gravity influences the movement of gases. Change that influence, and researchers can test models in a new regime. The immediate research may be designed for spacecraft fire safety. How do flames spread in a spacecraft? How does smoke move? How should fires be detected? How should materials be selected? But combustion research can also contribute to broader understanding. Again, the station begins with survival. Then the knowledge expands. Now consider fluids. A liquid in microgravity does not automatically settle at the bottom of a container. There may be no meaningful bottom. Surface tension and wetting behavior become crucial. This matters for spacecraft, fuel tanks, water systems, cooling systems, life support. But it also creates a laboratory for fluid physics. How do liquids move when buoyancy is reduced? How do bubbles behave? How do interfaces between fluids change? How can a system reliably separate gas from liquid? The answers become part of future spacecraft design. A journey to Mars will still need fluids. A lunar habitat will still need water. A spacecraft engine will still need propellant delivered where it is required. Microgravity turns ordinary plumbing into advanced physics. And then, advanced physics becomes ordinary plumbing again. This may be the most charming cycle aboard the station. A basic need creates a difficult scientific problem. The scientific problem produces new understanding. The understanding eventually becomes a machine that quietly performs a basic need. The astronaut sees a working toilet. The engineer sees fluid dynamics. Both are correct. Now consider materials. Samples can be exposed outside the station. Vacuum, radiation, atomic oxygen, ultraviolet light, thermal cycling. The environment tests them. A laboratory on Earth can reproduce parts of these conditions, but long exposure in the real orbital environment provides valuable data. Materials change, coatings erode, optical properties can shift, surfaces weather, engineers learn what survives. This knowledge helps future spacecraft. A material that performs beautifully for a short mission may behave differently after years. Duration reveals weaknesses. The station gives time to the experiment. This is one of its greatest resources. Not only microgravity, time in microgravity, not only vacuum, long exposure to vacuum, not only radiation, accumulated exposure. A station can host research that waits. Sometimes waiting is the experiment. Now consider biology. Plants can be grown in space, microorganisms can be studied, cells can be observed under altered gravity conditions. The immediate questions may involve future life support. Can plants contribute to food production? How do roots grow when gravity is not providing the usual directional cue? How does water move through a plant growth system in microgravity? How do microbes behave inside a closed habitat? But the questions expand. Plants are sensitive to light, moisture, nutrients, airflow, temperature, gravity. Remove or alter one influence, and biology reveals its flexibility. A plant aboard a station is not merely decoration. It is a small experiment in what life considers necessary. Humans often imagine that plants simply need water and light. Spaceflight corrects this simplicity. Water must reach roots without drowning them. Air must reach the plant. Humidity must be controlled. Microorganisms must be considered. The plant becomes another resident of the closed system, another source and sink, another participant in gas exchange. Future habitats may rely more heavily on biological systems. But biological life support introduces its own trade-offs. Plants need space, light, water, nutrients, care. They grow on biological schedules. A machine can sometimes be turned up. A plant has opinions, quiet botanical opinions. The station allows these relationships to be studied gradually. Now consider food. At present, crews still depend heavily on food launched from Earth. A truly distant, long-duration mission would benefit from producing at least some food locally. But growing food is not simply a matter of carrying seeds. The entire agricultural environment must be engineered. Light, water, nutrients, air, temperature, microbial control, harvest, waste. The station provides a place to begin learning. A small crop can reveal problems that a drawing cannot. Water behaves differently, roots behave differently. Crew time matters, cleaning matters, harvesting matters, taste matters. A plant that grows successfully but requires constant attention may not be ideal for a future crew with limited time. Again, the station turns theory into maintenance. This is one of its most valuable talents. Now consider robotics. The station is large. Its exterior contains equipment that may need to be moved. Visiting vehicles and payloads may require handling. Robotic arms provide reach. They can manipulate large objects in an environment where mass remains but weight behaves differently. A massive object in orbit can appear to float, but it still resists acceleration. Inertia remains. A robotic system must therefore move large masses carefully. Start gently, control motion, stop gently. An object that is weightless is not massless. This distinction is easy to forget until something large begins moving. The station's robotic systems have supported assembly, maintenance, cargo handling, and other operations. The unexpected benefit is experience with complex remote manipulation in space. Future construction may depend heavily on robotics, large telescopes, lunar infrastructure, orbital platforms, habitats, fuel depots. The station has helped teach engineers how machines can work outside a pressurized cabin while people supervise from inside or from the ground. Robotics reduces the need to expose humans to vacuum for every task. But robotic systems also have limits. A human hand remains remarkably adaptable, so the station uses both: people, robots, automation, remote control, different tools, different strengths. The future may belong not to one replacing the others, but to better combinations. Now consider Earth observation. A station designed to live above Earth also becomes a platform for looking down at it. From orbit, instruments can observe storms, clouds, land, oceans, atmospheric phenomena, cities, fires, agricultural regions, coastlines. The station's orbit repeatedly carries it over much of the inhabited world. The view changes continuously. A crew member can photograph an event, an instrument can collect data. The station becomes an observatory pointed not toward distant stars, but toward home. This is an unexpected reversal. Humans built a station to leave Earth, then used it to study Earth more carefully. Distance creates perspective. A river becomes a shape. A city becomes a pattern of light. A storm becomes a rotating structure. An atmosphere becomes a thin, visible layer near the horizon. The planet looks large enough to fill a window, and thin enough to appear delicate. This is where science and human perception meet. An instrument can measure, a person can notice, both matter. Crew photography has documented changes and events on Earth. Scientific instruments provide more systematic observations. The station becomes a platform whose location is constantly changing. It does not remain above one place. Its orbit carries it onward. Observation opportunities arrive, then disappear. Timing matters, geometry matters, cloud cover matters. The station is always moving, and movement becomes an advantage. Now consider technology demonstration. A new system intended for future spacecraft can be tested aboard the station. This is valuable because spaceflight is unforgiving of assumptions. A machine may work in a laboratory, then encounter vibration during launch. Microgravity, vacuum, radiation, thermal cycling, real crew operations, maintenance constraints. A station provides an intermediate step between Earth testing and a distant mission. The technology can operate in space, while remaining relatively close to support. If it fails, engineers learn. If it works, engineers learn something even more useful: how it works over time. This is how the station becomes an ancestor. Future exploration systems can be tested in the environment where some of them will eventually be used: life support, robotics, materials, computing, communications, human health countermeasures. The station does not need to travel to Mars to contribute to a Mars mission. It can test the habits required for distance. But perhaps the most unexpected benefit is not a particular experiment. It is continuity. For years, humans have maintained a continuous presence in low Earth orbit. One crew arrives, another leaves. Knowledge is handed over. The station remains inhabited. This changes the psychological meaning of spaceflight. A mission no longer has to be a brief interruption in human life. Space can become a place where ordinary routines exist: meals, work, exercise, maintenance, celebrations, haircuts, cleaning, sleep. The extraordinary becomes domestic, and domesticity is a technology. A species that can only visit a place has one relationship with it. A species that can live there develops another. Living creates questions that visiting never reveals. Where do you put everything? How loud is too loud? How do you maintain privacy? How often must filters be cleaned? How does equipment age? How do crews divide work? What happens when a pump fails at an inconvenient time? How do you celebrate a birthday? How do you sleep while machinery hums? These questions may sound smaller than rocket science. They are not. They are habitation science. A civilization beyond Earth will depend on them. The unexpected benefit of the station is that it has made space boring in precisely the way space needed to become boring. Not entirely. The view remains extraordinary. Launch remains extraordinary. A spacewalk remains extraordinary. But some parts of life in orbit have become routine, and routine is what allows attention to move elsewhere. If breathing required constant conscious effort, no one could conduct much science. If water had to be manually purified, cup by cup, the crew would do little else. If attitude control required continuous manual intervention, the station would be exhausting. Automation and infrastructure create cognitive space. The crew can think about experiments because the fans are already turning. This is the same gift infrastructure gives people on Earth. A person turns on a tap without studying the reservoir, flips a switch without operating a power plant, breathes without monitoring atmospheric chemistry. Infrastructure hides complexity. The station cannot hide it completely. The crew is too close to the machinery, but it hides enough. Enough for a person to wake, eat, work, exercise, look out a window, and sleep. This is perhaps the most unexpected benefit of all. The station has taught us that living in space may eventually depend less on heroic endurance and more on good infrastructure: reliable fans, repairable pumps, clear procedures, useful storage, quiet sleeping spaces, efficient recycling, interfaces that fit, machines that tell you when they are becoming unhappy. The future of human spaceflight may be built from spectacular rockets, but lived inside ordinary systems. Nothing up here happens by itself, yet the purpose of all that machinery is to make some things feel as though they do. The air arrives at the lungs, the water is drinkable, the lights turn on, the temperature remains comfortable. The astronaut can forget the vacuum for a while. And now our question returns. Why does a space station need fans to keep a sleeping astronaut alive? Because the fan is doing more than moving air. It is demonstrating the central bargain of habitation. The environment will not support you automatically, so you build a system that does. Then, if the system becomes reliable enough, you stop thinking about it every second, you sleep. That may be the true measure of infrastructure, not whether it can perform once, whether it can become trusted background. The unexpected benefit of the station is therefore knowledge about trust, how to build machines people can depend on, how to monitor them, how to repair them, how to live with them, how to recognize when a closed system is drifting, how to use waste as input, how to turn scarcity into cycles. These lessons do not belong only to orbit. They belong anywhere resources are limited, anywhere maintenance is difficult, anywhere people must live far from immediate support. A submarine, A remote research station, a desert settlement, a disaster zone, a future lunar base, a ship crossing an ocean, a habitat traveling between planets. The details differ, the pattern remains: air, water, energy, heat, waste, maintenance, people, loops. And this brings us to the final expansion. Because the station's pattern did not begin with spacecraft, long before humans built carbon dioxide scrubbers, long before solar arrays unfolded in orbit, long before a pump carried cooling fluid toward a radiator, nature was already building systems from cycles. Water moves through oceans, clouds, rain, rivers, soil, living things. And back again. Carbon moves, nitrogen moves, energy enters ecosystems and leaves as heat. Bodies regulate themselves through feedback. Cells maintain internal conditions. Forests exchange gases with the atmosphere. Earth itself is not perfectly closed, but matter circulates through vast interconnected systems. The station did not invent the loop. It miniaturized it, mechanized it, made it visible, and placed people inside. Now we can zoom outward, from one fan to one station, to submarines, cities, ecosystems, planets, and perhaps one day, worlds built by humans where no habitable world existed before. Let's go find it.